Let's hope this is not the only, but it's definitely the first U.S.-Sri Lankan Summit on graphite. And it's wonderful to be here. So I'd like to start with the opening ceremonies, and we will invite people up for this.
Okay. So to formally commence the proceedings, in keeping with Sri Lankan tradition, we invite our distinguished guests to light the ceremonial oil lamp. May I respectfully invite Fulbright Director, Dr. Patrick McNamara, Summit Chair, Fulbright Specialist, Adjunct Professor at Austin Community College, Professor Kusali Gamage, U.S. Embassy Economic Officer, Mr. Jake Thomases, Dr. Jonathan Thoma, representing the academic group. We also invite one representative from our industry partners to kindly join.
It is my pleasure to invite the Vice Chancellor of the University of Peradeniya, Professor Terence Madushit, Director of the Postgraduate Institute of Science, Professor Nanda Balasuriya, Dean, Faculty of Science, University of Peradeniya, Professor Sarah Rajapoksha, Director in International Relations and Head of the Department of Geology, University of Peradeniya, Professor Sanjeewa Rachi, excuse my pronunciation. Additionally, the Director of the National Science Foundation, Dr. Chandra Siri, and finally, DVC Professor R.W. Palagama. Thank you for coming up.
So may I now request everyone to kindly remain standing for the national anthems of Sri Lanka and the United States. Sri Lanka Mata, Apa Sri Lanka, Namo, 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 Namo Mata. Sundara Sri Marini, Surabhiyanti Sobhavana Lanka. Sri Santa Sadhana
Can you see by the dawn's early light what so proudly we hailed at the twilight's last gleam, whose broad stripes and bright stars through the perilous fight o'er the ramparts we watched were so gallantly streaming, and the rocket's red glare, the bombs bursting in air, gave proof through the night that our flag was still there. Oh, say does that star-spangled banner yet wave o'er the land of the free and the home of the brave?
It is now my pleasure to invite Professor Kusali Gamage to deliver the opening remarks.
Thank you, Iranji. Ayubowan, and good morning. It is my great honor to welcome you on behalf of the organizing committee to the inaugural United States Sri Lanka Graphite Summit here at the University of Peradeniya. It is truly a privilege to have such a distinguished group with us today, both in person and virtually. Academic colleagues, diplomats, government officials, industry leaders, and investors from Sri Lanka, the United States, and the broader international community. Before we begin, I want to take a moment to acknowledge something important. It took real effort for all of us to be here today. Over the past few weeks, there has been a great deal of coordination and flexibility behind the scenes. And despite shifting circumstances, you made the decision to be here today, to contribute and to be part of this journey. Thank you for your unwavering commitment. I would like to begin by expressing our sincere gratitude to our host, the University of Peradeniya, for welcoming us to this remarkable campus. We are especially honored by the presence of Vice Chancellor, Professor Terence Madhujit. I would like to thank the Department of Geology, especially Professor Malavia Arachi, for his partnership and support in making this summit possible. We are also deeply grateful to all our partners and sponsors, the University of Peradeniya, the Sri Lanka National Science Foundation, the United States National Science Foundation, the United States Sri Lanka Fulbright Commission, Austin Community College, as well as our very generous industry and individual sponsors. A very special thank you to all our volunteers from the Fulbright Commission, the Departments of Geology and Physics, the Summit Organizing Committee, and many other individuals. Although I cannot mention everyone individually, please know that your effort, time, and commitment are greatly appreciated. This initiative began in 2024 during my tenure as a Fulbright Scholar in the Department of Geology. What stood out to me at the time was the potential and the excitement in the graphite community in Sri Lanka to partner with the United States research and industry. We are today creating more than a meeting. This is a platform for partnership. We hope this summit initiates cross-sector partnerships across the entire graphite value chain, encouraging collaboration between academia and industry. As we know, strong, sustainable partnerships start with trust, transparency, accountability, and follow through. These are the foundations of lasting collaboration. So my hope for this summit is not just that we have productive discussions, but that we leave here with a clearer sense of how we move forward together, not just ideas, but action. With that, I thank you again for being here today, for your commitment and for helping us shape this important journey together. Thank you.
It is my pleasure now to invite Vice Chancellor Madhuchit to welcome us in this summit.
Good morning, ladies and gentlemen. The Chief Executive Director of Fulbright Commission in Sri Lanka, U.S. Fulbright Commission in Sri Lanka. The Summit Coordinator, Dr. Kusali Gamage from Austin College. The representatives from U.S. Embassy in Sri Lanka. The Director International Relations Office, Professor Sanjeev Malaviarachi, the Deputy Vice Chancellor, Professor Pallegama, the Director PGIS, Professor Balasurya, the Dean Faculty of Science, Professor Rajapaksha. Special thanks to delegates from USA, from various different states representing academia and US Geological Survey, and also corporate sector, other government officials, Sri Lankan officials from Geological Survey and Mines Bureau, students, invitees, ladies and gentlemen. First of all, let me thank the sponsors, Dr. Kusali Gamage and Dr. Patrick McNamara, who played a key role in making this happen, plus the Department of Geology, and currently headed by Professor Sanjeev Malaviarachi, who is also serving as a Director of International Relations Office. I can remember when we had discussions more than a year ago when Dr. Kusali came to Sri Lanka as a Fulbrighter. Along with Fulbright Commission, she initiated this, which was greatly assisted by the Department of Geology at University of Peradeniya. Well, University of Peradeniya is the oldest higher educational institution in this country. It's almost 84 years old, which was established in the time of British colonial era, way back in 1942. Now we have emerged as the #1 university in this country, ranked either #1 or 2 in the country, and also we have been identified as a first within the top 2,000 universities in the entire globe world. And the Department of Geology is the only fully fledged geology department in this entire country, which has produced a large number of geologists to the country and to the world. And they have started other universities where geology related courses are offered in this country, and I know many geologists, they serve in the United States as well. Well, I am happy to be here as a Vice Chancellor and also as a Fulbrighter. Thanks to US Fulbright Commission, I was a visiting scholar at University of Georgia, Athens, about 5-6 years ago. And also I have close ties with the United States anyway. I happened to do my master's and PhD in Canada, and during my graduate period, I frequently visited United States, at least 20 states of the United States. And my last visit was last August, where I visited Chicago, Washington, and also Athens. So this graphite, again, there's a relationship between Sri Lanka and United States in terms of graphite as well. Not now, long ago. The first graphite mining has happened in Dutch period in 1675, long ago, and commercial graphite mining has happened in 1800s. And the first commercial consignment of graphite has been purchased by United States way back in 1835. That was by a pencil manufacturer, Joseph Dixon, as I remember. He has purchased the first consignment of graphite. So in terms of graphite, we have a historical link, United States and Sri Lanka. And the University of Peradeniya has been immensely supported by United States. US aid program, I can remember when we were young lecturers attached to this university, through US aid, we received a large number of scientific equipment, consumables, chemicals, etc. And to the country, US has contributed enormously. Until quite recently, the World Food Program supported many schools in this country, just to name few. So thanks to people in the United States, you have been a great nation helping us throughout. Even during the most troubled period in the COVID aftermath, Sri Lanka unfortunately headed to economic crash, and there through IMF, United States immensely supported Sri Lanka, and that is why we are alive still, thanks to United States. So graphite mining, although it has happened centuries, the value addition has happened up to a certain extent, but there's much room for improvement. I know those who are represented in the industry, three main graphite mining companies, their representatives and chief executive officers are here. They would agree with me that value addition in terms of producing graphene and other battery grade graphite products started maybe 10-15 years ago. Still much room for improvement. Until such time we were exporting raw graphite, and Sri Lanka is producing nearly 1% of graphite requirement to the entire world. And the graphite requirement of the high purity, Sri Lanka is well known for the purest graphite. Although our production is 1%, our graphite is of the most fine form, which is ideal for battery grade graphite as well as for other value added production. For lubricants, especially, it is predicted that by 2030, the requirement of EVs, electrical vehicles, is enormously going up. For, of course, the graphite is an integral part of this lithium-ion batteries. So therefore, there's a very high room for us to produce value-added, fine quality graphite for the entire world. And it is not just extraction and value addition, but it should be done in a more sustainable manner. I know the world is faced with three different crises. One is an energy crisis. At least we have some solutions. Water, of course, a renewable energy. If we can carefully use them, of course, water also is not going to be a problem. But minerals is going to be a problem. Already has started as a problem. Much of the mineral resources in the world has already been exploited. So gold mines in Brazil and other countries in South Africa is nearly empty now. And much of this graphite itself is a carbon. It is again a mineral. It takes a long time to regenerate. So therefore, this mining also should be sustainable. So this kind of summit, as Dr. Gamage correctly mentioned, it's not just opens up for discussions, deliberations, but also we should bring this forward. How well the United States will definitely will help, I'm sure, in developing technologies, and also you will be one of the biggest buyers of our good quality graphite. And policy making, it is not just physical graphite, but the tariff system. There's a bit of economics here. Those also, our industrial policy, whether this is well aligned with our industrial policy, all these should be taken into consideration, not just the scientific facts of graphite and graphite refining. So this is an ideal forum, I would say. Thank you very much, the US delegates descending from all around the 50 states, from United States to Sri Lanka in this troubled period. And the Fulbright Commission, the Pat has already been a very good friend of University of Peradeniya. He's a very frequent visitor to University of Peradeniya. Thank you very much, Dr. McNamara, for your enormous support to University of Peradeniya. Department of Geology has taken the lead in organizing, and Dr. Gamage, who was a Fulbrighter about a year ago, who initiated this, got the assistance from all parts, from the NSF Sri Lanka as well as NSF United States and US Embassy in Sri Lanka. So I wish you a very productive discourse, deliberations today. Thank you very much.
Thank you for that introduction and that welcome. Now we have a virtual speaker, and our virtual speaker is Chairman of the National Science Foundation, Dr. Samarwira.
Very good morning, distinguished guests, esteemed colleagues and participants. It's my great pleasure as Chairman of the National Science Foundation to warmly welcome you all to the United States Sri Lanka Graphite Summit 2026, hosted at the University of Peradeniya. The National Science Foundation is partnering in this effort as a tangible outcome its strategic vision, advancing over the past several years our global digital platform initiative. Through this platform, we have systematically identified and connected with Sri Lankan expatriate scientists across the world, creating a dynamic network that enables knowledge exchange, mentorship, and collaborative research. This initiative has already led to several impactful engagements in capacity building, joint research, and international exposure for Sri Lankan scientists. Today's summit stands as a strong statement to what such global scientific connectivity that can achieve. The primary objective of this summit is to foster meaningful collaboration across academia, industry, and government, particularly in advancing graphite research and its sustainable utilization. As highlighted in the program, the discussion will span critical areas from graphite geology and petrogenesis to advanced applications such as rechargeable batteries and graphene research. Importantly, this forum aims to bridge the gap between scientific discovery and industrial application, which is essential for the national development at this very crisis situation in the country. The National Science Foundation is proud to be a co-organizer of this event. Our role extends beyond facilitation. We are committed to strengthening national research capacity, enabling access to global centers of excellence, and promoting collaborative innovation that aligns with Sri Lanka's development priorities. The Practitioners Forum we co-organized during this summit is one such effort to integrate research, policy, and industry perspectives into actionable outcomes. This summit has been made possible through our engagement with the global Sri Lankan scientific diaspora, particularly through the invaluable contribution of Professor Kusali Gamage. I would like to extend our sincere appreciation to Professor Gamage for her leadership and commitment in bringing this initiative to a success. I congratulate the Vice Chancellor and all academic and non-academic staff of the University of Peradeniya who have made an unwavering contribution to make the USA Sri Lanka Graphite Summit 2026 a successful event with long-term benefits. I would also like to place on record our deep appreciation to Kumara Kandanamulla, the Senior Scientific Officer, who served as the focal point at the National Science Foundation and played the leading role in coordinating and organizing this event on behalf of the National Science Foundation. Her dedication and meticulous effort have been instrumental in making this a reality. As we move forward, we are confident that the summit will open a new avenue for collaborative research, technology transfer, and innovation in the graphite and advanced material sector. More importantly, it will create opportunities for Sri Lankan scientists to engage globally, enhance their capabilities, and contribute meaningfully to national and international scientific advancement. Let me conclude by reaffirming the National Science Foundation's continued commitment to fostering such partnerships, strengthening human capital, and supporting science-driven socio-economic development in Sri Lanka. I wish you all a productive and engaging summit. Thank you.
Thank you very much, Dr. Samanavira. So it's my pleasure to invite Dr. Patrick McNamara of the Sri Lanka Fulbright Commission. Over to you.
Yesterday, as the American delegation wound its way up from Colombo to Kandy, we noticed on the roadside banana leaves spread out, red carpet, white carpet, many people dressed in white. Looked like they were awaiting some great pilgrimage coming through on this road. And as we came upon the monks and their dog Aloka, we realized we were encountering a walk for peace that had a vision that the globe should be one people. This started in the United States and has now come to Sri Lanka. Our bus stopped. We all got out. We're allowed in where the monks were resting, and on our knees, we praised them for the work they were doing. The head monk said, "Where are you from?" We said, "The United States." And Kusali said, he asked, "What state?" Kusali said, "I'm from Texas, and we have 4 of us from Texas." He said, "I'm from Texas." So immediately there was this connection. And at the end, we said, "We pray for peace." And he blessed us. I want to take that blessing from the monks walking across the globe for peace and offer it to the inauguration here today. May the next 2 days be blessed as bridges of peace between the United States and Sri Lanka and the world, because God knows we need peace right now in the world. The United States Sri Lanka Fulbright Commission was established in 1952. And the Binational Commission has 3 board members appointed by the President of Sri Lanka, 3 board members appointed by the U.S. Ambassador to Sri Lanka, and I report to that 6-member board of directors. I am the first non-Sri Lankan in 74 years to direct the Fulbright Commission. And it's a great honor and a responsibility, because we're looking for alignment with the national interests of both the U.S. and Sri Lanka. Graphite and what we're doing here is one of those areas of alignment. Our mission at Fulbright Sri Lanka is building bridges of understanding and peace between Sri Lanka and the United States through exchanges like Terence went on, through exchanges like you, Kusali, went on, through exchanges like some of the students in the back will someday be going on. Talk to me if you want to talk about a Fulbright exchange. We in this room can fulfill the purpose and mission of Fulbright if, out of the next 2-day conference, we can be bridge builders. Bridge builders of mutual understanding, peace, and ultimately mutual prosperity for both of our countries. Thank you very much for being here.
Thank you very much, Dr. Patrick. To conclude the opening segment, I invite Professor Sanjeeva Malaviarachi for the welcome and housekeeping remarks.
Thank you, Aranji. Very good morning to all of you. Welcome to the University of Peradeniya. And I would like to again welcome you on behalf of the Department of Geology as well as the International Relations Office of the University of Peradeniya. Your presence here is a great honor for us. Actually, I should take this opportunity to specially thank US Sri Lanka Fulbright Commission, Dr. Patrick. This is the second workshop of Fulbright specialist. We had one at the engineering faculty in last January. So thank you very much for your cooperation. And Professor Terence Madhujit, Vice Chancellor, thank you very much, sir, for coming here. And Deputy Vice Chancellor, Professor Ranjit Pallegama, despite all the commitments, you are here too. Thank you very much, sir. Professor Anath Rajapaksha, Dean, Faculty of Science, and Director PGIS, Professor Nanda Balasuriya, thank you very much for being here. Our colleagues, US colleagues, thank you very much. And our industry partners, academics, students, and everybody whose names were not cited, I warmly welcome you to this important summit. National Science Foundation especially, who voluntarily joined with us to organize the Practitioners Forum, which is going to happen at 2 p.m. onwards. Thank you very much for all your support, and I greatly appreciate that. As for housekeeping, I would like to just remind you some logistic points that you may need to consider. Locations-wise, facilities, we have washrooms or restrooms, just over here one, and more broader two are located on the floor below, just below this level. Refreshments will be served for those who have blue tag. For those who have blue tag in your name tag backside, please go to the place where named as cafeteria, just one level below. And those who have red tags behind, please go to the lobby, 2 levels below down, just the ground level where you entered this building. So lunch for those who have blue tags will be the cafeteria, 1 level below, and the others will be at the rooftop of the PGIS, which is the next block, but still you can walk from the basement, and you can just turn left and climb up to the rooftop. Unfortunately, we don't have a lift there, but for this building we have a lift. And we are planning to have a group photo just after the sessions in the morning and just before the lunch. So please gather at the in front of the lobby down there outside in the ground level. There we will have the group photo. And from 2 p.m. onwards, we have the Practitioners Forum, which is one of the most important sessions here today, because that will be a link to the industry partnerships. So please do participate in that and have fruitful discussions. And the poster session will be held at the Department of Geology, which is the next building just over there. You can go down to the ground level, the basement, and get out of this block and take the route from towards the right, or otherwise you can just get out from the lobby level, that is the next ground level to a left hand side, that is towards the botany building, and you can just go walk just 2 minutes away. So I hope this anyway you will be directed by our team, and I hope this workshop will be very fruitful one, and looking forward to listening your all talks. Thank you very much.
Thank you for all of that. I would like to just bring you up to date on a couple of things. I'll take a moment now to introduce myself. I'm Harold Stowell from the state of Alabama, and I'm very, very pleased to have been invited here by this esteemed crowd, and it's wonderful to be here to talk about graphite. And our first presentation in this series is going to be by Professor Wijayananda, History of Sri Lankan Graphite Mining. It's a pleasure to hear about the deposits that we are talking about so clearly today.
Good morning. Thank you for the opportunity, and made life easy for me because our chief guest, Vice Chancellor, he briefed about the history in his speech, so things made easy for me. And let me go through a couple of slides. The existence of Sri Lankan graphite was known since 1675. That was during Dutch occupation. Dutch was occupying our coastal areas. Previously it was Portuguese, then Dutch, then the Britishers came. And so the Dutch governor has mentioned in 1675 about this occurrence of graphite in his annual administrative reports. And mining also began in 17th century, and that's how the mining started, and then expanded during British colonial time. And most of our mines are concentrated in the southwest sector. If you go to the next slide. And these are, you saw some similar map previously or two. And these are the occurrences of graphite. I might not call mines, it's sort of pits. I'll show you some of the photographs. And you can see these are in sort of clusters. Now you get a cluster here, and then there's another cluster here, another cluster here. Likewise, and also if you go carefully observe these deposits, there's always a pattern, because these deposits, hydrothermal veins, are being included into the fracture system. And their behavior is, if you look closely, there's a pattern in it. On the fracture zone, it behaves something similar. So that helps us very much. That has helped us very much in exploration more than other usual techniques. And graphite is distributed in these 4 districts. Now these are the type of mines we had during Dutch time, and also late 1818 and also early 1900. And so they dig it, and because these veins are exposed, and at the backyard, if you get a graphite vein, there are people who collect graphite, and so they just dig it, and there's a limit which they can go down, likewise, because of the hoisting problem and water, pumping of water. So they might have gone about 100, not exceeding 200 meters because of these problems, hoisting and water problems. And this is the present status. This is from Wataraka Graphite Mine, courtesy of Mrs. Deepani. And so now if you visit these pits, if I may call, you'd see the pits like this scattered, and this is another one. And in exploration, we have to be extremely careful, because you'll realize that these areas are contaminated, because there's no rehabilitation as such. You can see the mining, and there's no rehabilitation as such. And what they do is, what they have done is, they have just dig it and pick the pieces, graphite pieces, and left the others. So any geophysical method, one has to be extremely careful, because you might get false anomalies, which we have experienced. Sometimes you get an anomaly, and when you drill it, you will see that it's a pocket of water and things like that. So one has to be extremely careful, and because the sites are disturbed and if I may use the word, contaminated. And if you look into the history, there were collecting centers. In almost every village, there was a person to collect these. And what people do is, they select the lumps and then put into the gunny bag and then sell to the collector. And at the collecting centers, what they do is, you get women who sort out like this. They have a bucket, a small bucket, and they select depending on the size of the piece, and then they pack it in drums like this, and transport was in this carts, sort of carts, and they sort it out here into this one, and then pack it in the barrels and then transport like this. So this is how it was mined during Dutch time and early British time too. And this is how they exported it. And if you look very carefully, you can see this has gone to New York. So they were exporting graphite even late 1800 to US. And there was a time called fledgling history. The earliest records of graphite being exported are in 1825, but previously also they might have been exported, but the records show 1825, with first commercial shipment occurring in 1829 to Joseph Dixon, founder of the American Crucible Company. The first official mention was 1831. So even early 80s, graphite was going to US, when it was included in the list of products subject to export duty. In 1832, the export revenue to the government was $22 US. That was during that time, early 80s. Due to its high carbon content, there was a growing demand for Sri Lankan graphite, particularly by the rapidly emerging crucible industry in Great Britain and United States, in part due to American Civil War. So that was basically the history. Early it was pits, I might not call mines as such, and they have mined to about 100 to 200 feet. And then at that level, they have done tunneling, of course limited. You might have seen the picture shows that they are not very safe mines. Accidents had been quite frequent, and sometimes they had even to close down the mine. And now we have 3 graphite mines. First one is the Kahatagaha graphite mine. You all will be visiting Kahatagaha graphite mine. And this was started in 1872. Then Bogala graphite mine is one of the country's oldest graphite deposits, discovered in 1675. It has been commercially mined by the Bogala Graphite Company since 1847. Then Ragedara mine. Ragedara also you will be visiting Ragedara. And this was mined since 1950, and it was closed down, and then again it was started in 2011. And right now, our export to the world market is about 1%, but there was a time during the 2 world wars, we were exporting about 1/3, 35% of the international market. We were supplying graphite during that time. And modern context is, current export is about 3,000 metric tons. This figure is 2023. Global demand is rising, as all of us know, due to electric vehicles. And graphite is classified as a critical mineral by US Department of Energy. I think I don't need to say, you all know about that. So it is a critical mineral. It has become a critical mineral. Then let me talk about a little bit of scientific side. Exploration, our experience is exploration has become increasingly difficult due to legacy of primitive mining practices. You saw that. Because the veins are disturbed to about at least about 100 meters. And then the surface is totally contaminated, and what they have done is they have picked only the lumps and left the rest on the surface. So it's a very high probability of getting false anomalies. And difficult due to legacy of primitive mining practices, abundant pits and environmental degradation. Then addressing these issues requires a proactive approach. Adopting modern exploration techniques, and of course in Sri Lanka we have airborne coverage only about 1/3 of the country, southwest sector. This was done in 1950s and digitized recently. Those data had been digitized, and but in picking this sort of clusters, one has to think about this, because when you plan a geophysical program, or airborne geophysical or drone-borne geophysical, one has to keep in mind that the surface is disturbed. And then strengthening environmental and community relations. Environmental, of course, yes, there, and community relations. And in mining sector, we have this social problem in Sri Lanka because our population is something similar to that of Australia. So you can imagine what sort of population density we have. We have one of the highest population densities. And so in mining is always become difficult. So that is an issue one has to tackle very carefully from the very initial stage. Of course, in the case of graphite, we are going down. So the area-wise, it is very limited. But we are having these problems in other sectors like mineral sands, where you have to disturb a large area. Community problems is there. And then limestone mining. And so that can be tackled, but one has to keep that in mind, the social issues, because of the high population density. Conclusion. Yeah, Sri Lanka's graphite industry has a rich legacy, but faces modernization challenges, which I mentioned. One is the expression and the social issues. With the global demand for critical minerals, Sri Lanka could reclaim its role as a leading supplier of high purity graphite. And we are quite confident that there are enough veins in graphite veins, but one has to explore them, and knowing the challenges, we have to find a way out for these challenges and also the social issues. Thank you. Thank you for your question.
Thank you very much for that synopsis of Sri Lankan mining history with regards to graphite. It's a very interesting presentation. We can take a couple of questions if there are questions from the audience. George, please.
Thank you for that interesting talk. You mentioned that there was geophysical coverage for about 1/3 of the country, and that was digitized recently.
Yes, that was digitized, but this was done in 1915, early 1950s, and they were in papers, sheets, because there was no digitization at that time. And so these were digitized at ITC Netherlands. One of our colleagues digitized this, and they are available at Georgia Survey.
Okay, thank you.
But the problem would be one has to think the resolution and picking up these veins. I expect the clusters to be picked up more than the type of veins, because the resolution would be not that adequate. Okay.
Okay, thank you very much. One more question, please.
Yeah, thank you for your very good talk. I have a question about what is being done or what is planned to be done with trying to bring all the information that has been available, been learned over the many hundreds of years about graphite veins and putting it together in a database that could be used perhaps to define the reserve.
What my first personal feeling is, because there had been registered the area which I showed, there had been 3,000, over 3,000 registered pits in that area, but definitely there were more than 5,000 pits like that which I showed you. So there was a high density of pits, which says that because when they were mining at that time, there was no exploration as such, and if you find graphite in your backyard, what they do is they start digging and go to a certain depth and then they abandon it. So graphite veins are there in small veins, but so those data, quite a bit of data are available at the Geological Survey, and get it, and then try to identify a proper geophysical method, how you can pick these. I don't expect the veins to be picked up, it would be sort of clusters and to be picked up. and then see to which depth they have mined and see it, because they might have gone to 100 meters, but not, I don't expect to beyond 200 meters because of the water table, high water table and the hoisting problems. So they have just abandoned it. So the material is there, one has to get it properly organized.
Sounds like that will be a great challenge. I think we're going to have to move on. I'm sorry, but due to time constraints, I believe we'll go on to the next talk. But I'm sure that we can have some additional discussions later.
Yeah,
Thank
sure,
you very
sure,
much.
Thank you.
Our next talk is Professor Malavayarachi, role of fluid mobility in graphite formation in Sri Lanka. Thank you.
Thank you very much. And my special appreciation to Dr. Vijayananda for presenting his expertise. And actually, he's one of the former chairman of the Geological Survey and Mines Bureau, Sri Lanka. And he showed the historical mine of Wataraka, and there the the current owner, the family member is sitting in the audience. So you can talk to her as well. Okay, let's start with the presentation. My talk is on role of fluid mobility in graphite formation in Sri Lanka. So in this case, I'm basically talking about sort of a review rather than my own data, but we are involved in similar research at the moment as well. So you can see the image here, which shows the occurrence of high quality vein graphite in Sri Lanka with quartz, and also you can see a layer of pyrite there that indicates the original fluid which involved graphite precipitation. Content, I'm first just briefing about the mineral, but I won't take much time on that. Then relevance to the Gondwana, because that is the last tectonic event that we suffered in formation of these deposits, and overview of the Sri Lankan graphite and the fluid interactions. So as you know, graphite is a sheet type of a silicate, sheet type of a mineral, which has vast applications because their structural characteristics. So the major geological origins of graphite, we have disseminated types. I think George was talking about disseminated types and flake type graphites, and also the other one is crystallization from hydrothermal fluids. That is what we have in Sri Lanka. If you compare the metamorphic versus fluid deposited graphites, there are so many advantages and disadvantages as well. In terms of origin, metamorphic graphite is ancient organic matter, whereas fluid deposited ones maybe contain a lot of volatile gases derived from mantle or even crustal fluids as well. Purity wise, it's a sort of medium for the metamorphic graphite, but fluid deposited vein type graphites are very high, even up to 99% of carbon. You can see now major mines up to this quality. As for the relevance with the Gondwana supercontinent, you can see here. You can see here the in the central part, the Sri Lanka is located here in the heart of the Gondwana, and there are several orogenic events which has. Is this okay? Which has given rise to several tectonic events, so that these fluids have migrated. Let's talk about that in the subsequent slides. So these major global graphite hosting provinces, for example, southern granite terrain, India, Mozambique belt, Madagascar, Brasilia belt, East Antarctic Shield, and the granulite complexes of Sri Lanka. So these all were together at the Gondwana, so that we have similar type of occurrences in graphite. So if you see the central Gondwanan graphite distribution, we can see here Sri Lanka, Madagascar, Africa, and Antarctica, also South America. So these tectonic blocks share similar features. Therefore, we can see as they are favorable sites for carbon mobilization. So fluid controlled graphite deposits, nearly 75% of global graphite resources were formed during the Gondwana amalgamation. So there has been a lot of potential for vein graphites in the globe, although we have explored only very limited areas. So these fluid mediated precipitations are mainly controlled by deformation and structural geological features, because the Gondwana is a time of intense dynamic. Earth's dynamic was intense at that time, so there has been a lot of fluid percolations. Just to compare flake versus vein, you can see here Molo mine in Madagascar, the top photograph, which shows flake graphite, and the vein graphites from Sri Lanka is just for comparison. So this fluid is mainly derived from mantle or otherwise as a metamorphic fluid. So these graphites which contain high purity carbon are mostly related with granulite facies metamorphic rocks. So in Bogala or Kahatagaha, we can see the high grade metamorphic rocks, that means high temperature metamorphic rocks, which host these veins. Actually, although these CO2 bearing, carbon dioxide bearing fluids which formed at high temperature conditions, they can be derived from the mantle, as I said before, and also there is possibility for derivation of them in the lower crustal conditions, because the lower crust is high temperature crust where a lot of pellitic type of sediments are there, and these sediments due to anatexis or the partial melting forms a lot of fluids. So these fluids can circulate within the vast depth of the crustal region, and also they can get mixed as we have witnessed from isotope data. So we will see the vein type graphite deposits and occurrences in the world here in this map. And there are two types also, actually, even for vein types, because some veins are hosted by granulite facies rocks that you see in red circles, whereas the stars, red stars, show igneous rocks hosted deposit. That means mainly the magmatic hosted vein graphite deposits. And also these blue stars indicates only the occurrences which are not deposits actually. They are not, maybe not economically extractable enough for economic purposes. Let's move to the Sri Lankan vein graphite, an overview. It's a unique type of a graphite because we produce the world's only high purity vein graphite, and also sometimes we refer them as lump graphites as well, and high carbon content. And as I said, they are located in the geological complexes called Highland and Wani complexes, where our key mines are located. In this map, you can see our active mines in this by these red triangles, whereas other graphite deposits are marked in black. In this geological map, brief geological map, where we have the Wani complex, which is having rocks of up to 2000 million years old, and the Highland complex is the oldest unit, which is going up to 3.4 billion years. There also we have these graphite deposits spread because of a lot of pellitic rocks are there, sedimentary, meta-sedimentary rocks are available there, and also during the Gondwana, these complexes, these units were in separate places where they collided and made high-grade metamorphism. During that time, just at the late stages of the metamorphism, these graphite fluids were acting within the crust. If you see some of the occurrences of the veins of graphite, and here from Kahatagaha mine, you can see the vein is moving, and also it's branching as well. So this indicates heavy deformation conditions because while these high temperature conditions are there, rocks behave in ductile behavior, so that they can easily create shear zones and other weak, tectonically weak zones, so that these fluids can easily migrate. And also you can see from Bogala also, this particular graphite vein is having some calcite as well. So this is a very characteristic feature in Bogala, where we can see very rare occurrences of calcite as well associated with the graphite. And again, the same picture that I showed at the cover slide, where graphite vein with quartz and pyrite, probably this show some liquid immiscibility conditions, where the original fluid separated non-mixing other fluids and later crystallized within the system. This is from Bogala. And also the fluid migration, you can see there are different characteristics with respect to these veins, and also they react with the country rock also in some places. So I will show some evidence for that. And also you can see here the high grade metamorphic rock, pellitic metamorphic rock, condylite or garnet sillimanite bearing pellitic rock, metamorphic rock, where you can see which is hosting this graphite vein. And these host rocks contain a lot of fluid inclusions as well. So these fluid inclusions indicate original fluid that contributed for this graphite precipitation. And also you can see the sillimanite occurrence there. That means very high temperature conditions were there, so that even these anataxis or partial melting conditions can trigger this graphite precipitation due to various types of fluids. And also we can see here the occurrence of garnet in Bogala, large garnet, and also some fluid inclusions. And also there are some hydrous mineral crystallization, which is related with the release of the water after redox conditions change during the graphite crystallization. If you check the graphite crystallization reaction, one of the reactions, you will see hydration is happening there. So these hydrous materials can contribute to biotite-like minerals later on. And the graphite veins here, you can see high temperature to ultra high temperature conditions were prevailing in the region, and they contain high density CO2 fluid inclusions, and also these some of these veins are related with micro shear zones. For example, this BGM1 means the Bogala, one of the Bogala samples, which contains a minor shear zone here that indicates the tectonic conditions or deformation conditions existed during this graphite crystallization. And also there is some fracturing evidences like vein bulging when the when the fluid is intruded, it can bulge due to pressure differences. So these are some examples of this fluid migration related with graphite crystallization. And some more aqueous and CO2 fluid inclusions, which are very, very abundant in these graphite bearing rocks. And some inclusions are intragranular and some are intramineral. That means within the mineral itself also we can see inclusions as well as in between the minerals, particularly along the grain boundaries. So these are the evidences for our paleo fluid investigations. And also some low salinity conditions have been also reported, like 2-8% of sodium chloride in these fluid inclusions. So that means this graphite crystallizing fluid has changed its conditions or the chemistry throughout the time probably. And also here again some fluid inclusions and in the host rock as well as in the vein. This is the graphite vein, the black one here, and you can see in contact with that there is a big quartz grain, and inside the quartz also some fluid inclusions. This square is expanded here in the B. There you can see CO2 and water fluid inclusions. Also you can see graphite as well within the quartz itself. That indicates this quartz has grown with the evolution of this graphite crystallizing fluid. As for the sources of carbon for this graphite crystallization, the main candidate is the mantle derived CO2, and also there is possibility for biogenic contributions of carbon due to high temperature metamorphism, and of course later on all these fluids can get mixed as well. That is what we see from the stable isotope values, which are having different end members. And the graphite forming reaction here, as I said before, it's a reduction, or the redox conditions are changing. CO2 reduces to carbon basically, and also methane can be involved there, and water is also formed. That means it's a hydration. That's why we see some biotite inclusions associated with this graphite form. And since these are showing a sort of mixed isotope composition, here for example towards the carbonates end, that means more metamorphic site, and the biogenic end, that is ancient sediments, and also the mantle values which are lying here. Although there are considerable number of samples show mantle values, we have still the mixed ratios observed. That means all these fluids must have mixed during these intense tectonic events during the late stages of metamorphism. As for fluid chemistry, as I said in previous slides, it is CO2 rich fluid and also high salinity brines, and aqueous fluids are also involved there because we see the water and CO2 inclusions together. And also there are metasomatic changes in surrounding rocks while this fluid is migrating, because it is exposing to different PT conditions. Therefore, based on the depth in the crust, these fluids can react with the host rock. So there are several metasomatic reactions, especially associated with faults and shear zones because of these fluid infiltration. And if you see closely the Kahatagaha graphite mine, for example, this is a local geological map. At a larger scale it is drawn, and you can see the the folding actually in this region, we can observe folding. This is antiform. This is so-called Dorangasland antiform, which is a folding structure, so like this. And associated with these folds, there are a lot of weak zones can develop. So that's why this graphite is concentrating along these weak zones. The theoretical explanation is given here, so that you can see how these shear zones as well as fracture zones can be generated, so that these fluids can be facilitated through those weak zones, tectonically weak zones, as a pathway. And mainly the decarbonation reactions in the mantle may have caused this CO2 to come up, and also having brines would have enhanced some dissolution and precipitation processes, so that this carbon can be easily crystallized. Also, this precipitation based on the petrological evidence and also geochemical evidence has happened at the late stages of the metamorphism, peak metamorphism. So peak metamorphism is here in these complexes, which is high temperature and also ultra high temperature partly. So during the decompression, this is the decompression, the PT path. During this decompression, these folding and weak zone generation is happening, so that these fluids can migrate and easily precipitate graphite, because the crustal rocks are now experiencing cooling as well, while the decompression is also taking place. So this is the cooling combined hydration reactions happening in the host rock, and where the fluid precipitate graphite there. Yeah, sure. And some of the metasomatic reactions you can see here. So I think as for the conclusion, we can say that Sri Lankan graphite is fluid precipitated, and it's not just formed by heat and pressure, but active circulation by carbon-rich fluids, and obviously the process is deformation controlled, and a combination of mantle-derived carbon, high salinity brines, and rapid tectonic uplift. All these three is kind of a unique combination for collectively form these high quality crystalline natural graphite. Thank you very much.
So I'm happy to introduce our last speaker in this group of talks. And our last speaker in this group is Professor Balasurya, carbon-rich fluids, battery-grade carbon, geological controls, processing pathways, and technological potential of Sri Lankan vein graphite.
Yes, good morning, ladies and gentlemen. Yes, this is the presentation is mainly based on research carried out last 15 years, and research highlights and key points and milestone and way forward. And basically start from discuss about the origin of graphite. Professor Sanjeeva explained, and Professor George explained, and in a world state of how to form graphite, and Professor Sanjeeva explained how to fluid generate and fluid migration. And thanks both them to make it easy for to explain this one. And this is a collaborative research in Department of Geology. Thanks to the department colleagues, and also special thanks to the members of the team. Dr. Gayani is here, Himashi, and Atul Vijay Singh. And Atul Vijay Singh has passed away in March 2026. And this percentage is dedicated in his memory, his recognition, his unwavering commitment, and invaluable contribution leading our research group. And I wish to attend his Nibbana. And with this one, I'll go ahead with this one. Yes, this is one of the pictures taken from different level of Kahataka graphite. And you can see the lowest level that what we are collected samples from 565 to almost 2000 feet levels. And Professor Sanji also mentioned that yes, you can see this picture, first one, and A, that is the lowest level, say 565. Then D is the same vein, it's continuous from the deepest level, and you can see the veins intruded through these faults and fractures. And it can be in thickness of the vein is a few meters to tens of centimeters, few centimeters to tens of centimeters. And you know that vein graphite is very unique in Sri Lanka. It is a high purity, about 95 to 99, and also high crystallinity and mode of occurrence. That's a very unique of this Sri Lankan vein graphite. And yes, this is my presentation mainly focused on at the beginning in 2005, 2006, we started the research to identify different morphologies of graphite. In the same way, can see the unique varieties are there. Then we label it based on their physical properties and chemical properties, and also microstructure. Then can be classified as 4 different varieties, and it was published in Canadian Mineralogist in 2010. And our whole research start from that point and carried out even the chemical purification using chemical treatment and surface modification, all based on the all varieties. Now we are in a state, we are now scaling up this all our findings. And also we proved that one, this is what George just mentioned, this is a multi-stage of mineralization. Not a single vein, it's a multi-stage of mineralization. You can see this picture in this one, you can see that this one of the indicator is that you can see different type of varieties, so sharp contacts and form in different stage of intrusion into the vein. And these are some of the evidences of the vein. You can see here that it's a fibrous formation of graphite in the wall rock. And then again, B is a thicker vein, about 120 meters. And what Professor Sanjay mentioned, some places vein can bulge in the way, and not in evenly distributed. And some of the formation morphologies are formed as we call coarse flake of radial graphite also there. And when you talk about the origin of graphite, this is already in the KL panel 1903-1905. Unfortunately, we missed this presentation today, but his mainly initial hypothesis about the magmatic origin. Later, that all this in our group we categorize in vein graphite in 4 morphological varieties. Then we describe that it form a different hydrothermal fluid invasion in different multi-stage. And conclusion of this origin, what Professor Sanjeev also mentioned, that's about this origin of this mantle derived carbon fluid. Yes, it's Professor Kehalpanna also mentioned it form a composition of it contain carbon, hydrogen, oxygen, sulfur-rich magmatic solution as hydrothermal invasion to the vein graphite involves in a complex magmatic process. And still ongoing research are going on for the understanding of his unique mineral. And this is again this wall rock alteration is a critical indicator of hydrothermal process in controlling graphite mineralization. And this is indicate that you can see this picture, even Professor Sanjay has shown these publications, and even this graphite vein, you can see several centimeters far away from the vein, you can see the wall rock alteration. It indicates alteration signatures indicate the hydrofluid pathways, and wall rock alteration linked to the graphite precipitation process and structural control and fluid evolution influence or formation. And this is a chemistry and a geochemical signature and purity of different types of graphite. A indicates the lower level about 565 in Kahataga, then deeper level is indicate D. Then all this carbon contains almost 99%. When these are the other impurities, and mainly impurities coming from the minerals like gangue minerals. And it's important to do the chemical purification. When you go for the high-tech application, even battery application, we have to further treat this graphite. therefore, we really focus on this treatment of graphite. Mainly, we thought go for the chemical treatment, and we recommended to go for that. We tested initially in acid leaching, then alkali roasting, and finally we identify we have to think about the combine these two processes. That means acid leaching followed by the alkali roasting. Then we can purify vein graphite to up to 99.9. Then it is ideal item, ideal material. Go for the battery applications. Okay, these are the method what we tested purification method. Initially, we start from flotation, then acid leaching, alkali roasting, then surface modification followed by this acid leaching and alkali roasting, ball milling, thermal oxidation, then oxidation, chemical oxidation with nitric and H2O2, then lithium carbonate coating method. Then you can see the different varieties how enhance their carbon content. Then these are the challenges. These are when you use these chemicals, we have to think about this, how to make in a disposal of this waste, and then again environmental compliance are there. Then other problem is high operational cost. And we have to think about the sustainable approaches, and we recommend and promote alkali roasting plus low acid leaching combination. And we can think about the closed loop of chemical recycling system, and also we can think about how we can go for the green purification technologies like bioleaching, thermal purification using renewable energy. But anyhow, finally we have to adapt the environmental regulation and incentives. Okay, this is the final research here, what we have carried out and published. The first lithium half cell assembles, and these are the in NIAPS, a collaboration in NIAPS, National Institute of Fundamental Study, established battery testing unit. And thanks for the government of Sri Lanka, NRC and NF contributed this develop this unit. It's now full function, that one. And these are the some equipments, glove box and battery testers are already established there. And now we research is going on, and mainly that we develop this one after chemical treated graphite can be used for the lithium ion battery. And this is a concept of battery, everyone know that is concept cathode, anode and overall. And mainly we initially start to assemble the half cells, lithium and graphite. Then finally that we successfully develop a cathode material and use the graphite as anode. Okay, all these findings were published, and some patents published, and also it was a patent in Sri Lankan patents, and some of the patents now we are in a way to commercialize. Okay, then we thought to go for the NIBs, that means sodium ion batteries. One of the main barriers, not like in lithium ion batteries, we have to expand this interlayer spacing. For that one, we expanded graphite and use testing for the NIBs also. Then for this one, we use this synthesis of thermally RGO, and this is the process what we recommended, and it was published. And this reduced graphene oxide or graphite oxide can be utilized for the solid NIBs. And this is what we recommend. We start up on raw material, now purified graphene oxide, then it can convert to the graphene derivatives, and we can use for the advanced device material. And this is a way we can move from mineral exporter to nanomaterial producer. Okay, another option we can think about the deal of the spherical graphite from Sri Lankan graphite. We can start the process, they are there, well established process. Start from raw graphite, micronization, spherization, then purification, then we have to carbon coating, that's called finally coated spherical graphite. And that's one way we can think about how to move forward, and Sri Lankan vein graphite used in the battery industry. And now we are exporting as a raw mineral, exporting, but somehow this value added to the, that means powdering. But it is not real value added, but we have to think about the how to we can supply this battery grade graphite into the world EV supply chain. That should be our target. And yes, another option we can think about the graphene in lithium-ion batteries. Graphene, as in graphene, we cannot use as a lithium batteries. It should be making a composite. That whether graphene, we can mix the silicon or graphene mix with the graphite and making a composite. It can be anode. Then what are the main challenges when you're using the graphene in lithium batteries? Their cost, high production cost, because develop the graphene, you have to make in the CVD or chemical exfoliation, or that is the main is the high production cost is the main issue, challenge of when you are producing graphene and when you are using the graphene in the LIBs. Okay, these are the challenges and recommendation and way forward. And we have done enough research. We have findings. Now problem we are working on scale up. Now next step we have to go for the pilot plants. Now this is a problem, say how to invest. That is the issue what we are in Sri Lankan. We have done. We have a lot of research publications are there. There's no step to go forward. Then I recommend at least we can take this position and discuss in further how we can go for next step using this Sri Lankan graphite and using a premium battery grade graphite supply in the world. And balancing point, optimize hybrid purification method that achieve required purity while minimizing environmental footprint and cost. And research to industry linkage, that's one of the challenge, one of the lack step in Sri Lanka. That we have, what I mentioned earlier, we have strong academic research output, but its problem is commercialization. Now, this another point that is current gaps, weak industry, academia collaboration, that is a lack, and limited private sector investment in advanced material, lack of policy direction in value-added graphite products. Key strategies, establish PPP, public-private partnership, and thanks to the Minister of Industry, now it's already advertised for the Kahataka graphite. It's a state-owned company, and chairman also there. And now we call for PPP, and create a national graphite innovation hub linked with the universities and industry, provide government incentives for downstream the graphite processing, encourage technology transfer to start up new battery materials. Yes, my main vision and strategic vision that move from exporting raw material into exporting battery ready materials. And we can integrate Sri Lanka into the global EV supply chain. That's my recommendation, and I hope we can achieve that if we work together as researchers, universities, and industry people here. Bogle Graphite CEO is there, Jai Singh, and also Mr. Kirti, Ragidra Graphite, and also Bogle Graphite Chairman, Mr. Hemalal. I hope we can work together, and also investment is there, investors and scientific experts, and we can work together and think about a positive way to go for this strategic vision. Thank you.
Thank you.
Well, thank you to all our speakers for an excellent session. And we now move to session 1B, focusing on geochemistry and metamorphism. Our first speaker is Professor Emily Stewart, who will speak on decarbonation and the carbon cycle.
Awesome. Thank you all so much for being here. I'm really excited to talk to you about some of this work. I'm going to give you kind of a different perspective on this same processes, just another reason that we want to care about metamorphic fluids cycling around in Earth's crust. And so to get into that, I'm going to start by zooming out just a little bit and thinking about planet Earth. And Earth has had life for at least a couple billion years, right? Whereas our nearest neighbors of Venus and Mars have climates that are far too hot and far too cold, respectively, to support life as we know it. So Earth has this kind of Goldilocks climate that allows us to have life over long time scales. And the primary reason for that climatic stability is the global or geologic carbon cycle. So these are the series of processes that move carbon back and forth between the solid Earth and the ocean atmosphere system, ultimately regulating the amount of CO2 in the atmosphere, the strength of the greenhouse effect, and making our climate habitable. And we can really broadly divide this cycle into sources of atmospheric CO2 and sinks. So sinks of CO2 would be primarily silicate weathering. So, taking carbon out of the atmosphere, reacting it with calcium to make carbonate minerals, and drawing down calcium that way. But I want to focus today on some of the sources of atmospheric CO2 on geologic timescales. In particular, I'm interested in metamorphic carbon dioxide release. So this is a figure showing different carbon fluxes that we've estimated recently. And what you'll see is that metamorphic fluxes are around the same order of magnitude as fluxes associated with volcanism. Classically, we tend to think of mid-ocean ridge volcanoes and hotspots and volcanic arcs as the big source of CO2, but in fact, rock metamorphism is an equally important process. The other thing that I think is interesting about this is that these solid colored bars here in the metamorphic areas, these are surface measurements. So these are, for example, surface measurements made in the modern Himalaya or Italian Apennine. And those measurements of how much CO2 is being released at the surface are comparable to our estimates of how much CO2 is being generated at depth, which suggests that a lot of this metamorphic carbon fluid is ultimately making it to the surface where it can interact with our climate system. And just really quick to be really explicit, this is not an explanation for modern global warming. All of the volcanoes and metamorphism in the world come up to something like 1% of human carbon emissions. So this is an important process over millions and billions of years, but it does not explain what we're seeing on Earth today. So in terms of the pathways to release carbon from a metamorphic rock, we've already seen some of this, but I'll just go through quickly. Carbonate devolatilization is one pathway. In these reactions, you generally have some silicate material, in this case quartz, reacting with some carbonate material, in this case calcite, to make a new calc-silicate mineral and release CO2 gas. So this is a nice, simple reaction that we like to show. In fact, wollastonite is not particularly common on Earth, but there are more common decarbonation reactions that are similar in that they're driven forward at high temperatures and they require both carbonate and silicate as reactants. And this is a graphite conference, so I'd be remiss if I didn't talk about how we devolatilize graphite or organic matter during metamorphism. And this is going to be a fundamentally redox sensitive reaction. We need to take neutrally charged carbon, whether that's in graphite or sedimentary organic matter, and we can either oxidize it to make carbon dioxide, or we can reduce it to make methane, but either way, you've got to combine it with something else to drive these reactions. So with that background, I'm going to tell you two different stories about metamorphic carbon behavior on Earth and how it might have interacted with our climate system. And I'll begin by talking about our evidence for enhanced metamorphic carbon release on the early Earth. Moving back to this decarbonation reaction, you remember that we have both silicate and carbonate material driving this reaction. If we just had a pure calcium carbonate rock, we would not be able to release any CO2, or at least much CO2 during metamorphism. So we can do a little toy model and imagine two sedimentary sequences. One that is unmixed, where you have a pure calcium carbonate layer on top of a clay silicate layer. Or we can imagine a different setting where that carbonate and silicate are mixed together and able to participate in reactions during metamorphism. So we can forward model how much carbon would be released by these different compositions. So here I'm showing the percentage of CO2 released as a function of the rock composition. Moving from a rock that's pure calcite, as predicted, there's zero CO2 release happening in that rock. But as we increase the percentage of clay present in the rock, the amount of CO2 release increases until we get to a rock that's about 90% clay, 10% carbonate. That rock can undergo 100% devolatilization at the exact same pressure temperature conditions where we saw no devolatilization in a pure calcite rock. So the carbonate silicate distribution really matters for metamorphic decarbonation. It turns out that the specific carbonate mineral that's present also matters. Calcite is our calcium carbonate mineral, dolomite is a calcium magnesium carbonate mineral, and in silicate limited systems, dolomite is going to begin reacting and releasing CO2 at substantially lower temperatures, and it's also going to end up with about twice as efficient CO2 release. So calcite versus dolomite mineralogy really matters. And finally, the temperature over pressure ratio matters. Temperature drives these reactions forward, but pressure suppresses these reactions. So at a given temperature, depending on that temperature divided by pressure ratio, we can have very different degrees of decarbonation. In a low temperature over pressure path, so like a relatively high pressure scenario, you have less decarbonation than at the exact same temperature, but at a lower pressure. All right. So with that in mind, take a moment with me. You can close your eyes if you like, and imagine a perfect world for maximum metamorphic decarbonation. If you're like me, you're imagining a world that has more mixed carbonate silicate rocks, a world that has more dolomite than calcite, and a world that has high temperature over pressure ratios during metamorphism. And there's reason to think that these things have changed over the course of Earth history. Right? Today, carbonate is primarily deposited by little critters making their skeletons out of calcium carbonate and sinking to the bottom of the ocean. But those little critters evolved about 500 million years ago. Before that, carbonate sedimentation was almost entirely abiotic, and it would have been restricted to continental shelves where you have more silicate input and just a very, very different depositional environment. So I looked in the literature and found some of these big data compilations. This paper by Cantine and others is compiling observations of all the Precambrian carbonate rocks they could find in the literature, while Holder and others are looking at changing metamorphic temperature and pressure conditions through time. So looking at these papers, we can think about what was the Precambrian Earth like. Well, on the top here, I'm showing how sediments are changing through time, and you can see there's a pretty distinct peak in the percentage of these mixed carbonate silicate type sediments around the Mesoproterozoic. There's this well-known observation of much more dolomite on the early Earth as compared to calcite. And in addition, metamorphic temperature over pressure ratios were likely higher on the early Earth and have been cooling over the last 1 to 2 billion years. So what was the Precambrian Earth like? More mixed carbonate silicate rocks, more dolomite, higher temperature over pressure metamorphism, maybe a perfect world for maximum metamorphic decarbonation. So I did some kind of simple forward modeling to think about how carbon fluxes would change through time, and I generated this curve. This is only changing as a result of those changing sediment compositions and changing metamorphic pressures and temperatures. And we find that there is, as you might expect from those data, a peak in the middle of the boring billion and the amount of CO2 that would be released by the solid Earth. I passed this off to my friend Don Penman, who is a carbon cycle modeler, and he put my carbon flux into his carbon cycle model to see what the effect on the atmosphere would be. And that's what's shown here. And you can see there's something of a magnifying effect. So even a 25% increase in CO2 degassing can lead to a six-fold increase in atmospheric CO2 concentrations. So this is a pretty major effect. The other thing we weren't expecting, but which is kind of intriguing, is that this time period when we were predicting the highest PCO2 values is during this boring billion that George mentioned earlier. And that boring billion is a period where there were no global glaciations, right? About 2.2 billion years ago, there was a near global glaciation. Then there's a billion years with nothing, and then you get another global glaciation at 700 million years ago. And I don't think there's been a very good explanation for why we see this relatively warm period in Earth history. And I would suggest that enhanced metamorphic decarbonation is at least a plausible explanation for why Earth was unglaciated for billions of years. So this is all a model. I have an ongoing field test going in the Grenville province. This is led by two of my PhD students, Kanos and Gupta and Sayant and Saha. And I think I am not going to have time to talk about those results, but I'll just kind of skip forward on the work they've been doing. And the takeaway from this portion would be that the modeling predicts enhanced metamorphic CO2 release in the Proterozoic. which carbon cycle models suggest could contribute to a warm deglaciated Earth. And our preliminary field results support that modeling with about 2 times greater CO2 degassing in the Grenville as compared to a more recent orogenic event. All right, how much time do I have? So I would talk really briefly about carbon release and mass extinction events. This is an artist's rendering of what you would have seen if you had been unlucky enough to be alive during the emplacement of a large igneous province. These are these massive outpourings of lava and emplacement of magma on Earth. And it's long been recognized that there seems to be some relationship in time between when a large igneous province intrudes and when a mass extinction event happens. So this has led to the very reasonable hypothesis. Perhaps these massive, hellish, igneous provinces are driving those mass extinction events. There's an idea out there that perhaps it's not actually the volcanic degassing, but rather catastrophic contact metamorphism, devolatilizing organic-rich carbon sediments, and putting that carbon into the atmosphere that is driving catastrophic global warming and mass extinction events. So I've been working on the relationship between the Central Atlantic Magmatic Province, this is our home large igneous province in North America, and the end Triassic mass extinction, which took place about 200 million years ago. Modeling predicts that there could be really massive amounts of carbon release associated with this large igneous province. Forward modeling by Heimdall and others finds that they predict, really efficient carbon release next to these very hot, high-temperature magmatic intrusions. So this work is being led by my PhD student, Lindsay Allman, in collaboration with some folks at the USGS, including Rebecca Stokes. And we've been looking at specifically rocks from the Florida basement. And what we found was kind of a whole lot of nothing. The carbon isotopes that we see don't really change much as you approach the sill. They kind of stay in that normal sedimentary organic matter range. The amount of carbon in the rock, the total organic carbon, again, not really changing, kind of just sitting there around like 1 weight percent. But what we do see is that the carbonate is behaving a little more interestingly. There's almost no carbonate below the sill, and then this very carbonate-rich layer at the top of the sill. When we look at those rocks, we see this big sea of iron carbonate that's being precipitated around the igneous plagioclase crystals. And so we think that there was a lot of carbon being mobilized from these carbonate minerals rather than from the organic carbon. The organic carbon, by the way, is present in the form of chitinozoa that's been partially graphitized, but is still very much present in these rocks. So based on some modeling, we think that the high activity of CO2 in these rocks might be suppressing devolatilization. We have Andalusite pseudomorphs, so we think these rocks reach temperatures in excess of 400 degrees Celsius. If these rocks had evolved in a closed system, which is what's shown by this red line, this modeling predicts that there should be no graphite left. They should be completely devolatilized, which is not what we observe. But what we do see is that there is a high, if you have a high activity of CO2, you can keep graphite stable up to those very high temperatures. So perhaps this presence of carbonate is actually stabilizing graphite and ultimately aiding organic matter graphitization because it's able to stick around at those higher temperatures. In general, our field-based estimates of how much carbon is being released by these processes are substantially lower than models. Models predict much more carbon release than what we observe in the rock record. So some conclusions from this part would be that our rocks record less than 30% of the degassing that would have been predicted solely by modeling, and that amount of degassing is unlikely to drive any major climatic effects or mass extinction events, although it's unclear if this is representative or if this is just an oddity of kind of the rocks we've been looking at in the Florida basement. And with that, I'll share these pretty rock photos, and maybe I have time for questions. No.
Well, thank you very much for that informative presentation. Now we invite Professor Harold Stowell, who will discuss carbon mobility during metamorphism with an example from the Alabama Graphite Belt.
Well, thank you for joining me this afternoon. I guess, is it afternoon yet? Well, I think we're moving on towards lunch. I'm going to talk to you today about a very specific example of carbon mobility, and I'm going to conclude that it's limited. But what I want to also state is that this is an example of tying the chronology of graphite formation with metamorphism, and so I'm going to indicate how that works. And I'm also going to think about it very briefly at sort of a tectonic scale and discuss how we can actually use the tectonics and our tectonic setting and the metamorphic variation as an exploration tool. So first I'll talk briefly about carbon mobility. We've discussed that quite a lot, so I'll go through that quickly. Talk a little bit about Southern Appalachian geology, and that's also been introduced, so I will move rapidly. But then I want to concentrate on the metamorphism and the timing of metamorphism and carbon mobility and flake graphite formation. So as discussed very well by some prior speakers, long-range mobility is going to be facilitated by either producing CO2 or methane. And reduced methane is pretty common in marine sediments, so we can see it coming out of cold seeps and percolating out of sediments throughout the world. Oxidized CO2, of course, as was pointed out by Emily, is being produced in many metamorphic reactions, and we see that in lots of places. And of course, examples of it are seen in fluid inclusions, as was very well documented in some of the metamorphic vein deposits or mantle vein deposits, whatever you want to call the Sri Lanka deposits. We see lots of wonderful fluid inclusions with CO2. So we know that that is one of the sources of carbon mobility. So we see that worldwide, and we see also, of course, textural and isotopic evidence for devolatilization. And Emily pointed out very clearly the production of elastonite as calcite reacts with silica. Well, of course, lots of silicate minerals are solid solutions, so it's not always going to be elastonite. It's going to be some more complex pyroxene or other type of mineral, but there's going to be devolatilization from the carbonate minerals. So going on to the specifics then, so I want to emphasize that the Appalachian orogenic belt is not nearly as simple as, in quotes, simple as the Himalaya or other contractional mountain belts. It's a polyphase metamorphic, multiple deformation and multiple contractional event origin. So it's not easy to go and say, well, we know that metamorphism occurred at some age throughout the belt. That's not the case. In fact, many rocks have undergone multiple events. So it's a very complex and very large origin. And this map from Hank Williams way back in the 70s, late 70s, shows you the North American part of it going from Newfoundland down to Alabama, and of course along the eastern seaboard of the North America. And then there's an inset map here which shows the part I'll concentrate on in a minute, which is the Alabama portion. But if we look a little bit more detail at the Southern Appalachians first, it's of course the compressional, contractional orogenic belt. It has multiple segments from across the origin, from foreland fold and thrust, which is dominantly sediments which have been folded and faulted, into the metamorphic core. And so in this case, the tan color that you see on the northwest is the fold thrust belt. And it's all of these other colors that are of interest when it comes to graphite. If we look more carefully now at just the Alabama portion, all those colored fragments or colored segments that you see there are what we call the Western Blue Ridge. And that's where the high-grade metamorphic core of the Southern Appalachians. It's not simple because, again, this is not a place where you can say all this occurred at the same time. Not at all. Nor did all of these different thrust sheets undergo the same temperatures of metamorphism. But nonetheless, that's what we have to deal with. If we map out what we know about metamorphic zones, which in the Southern Appalachians is only moderately understood, surprisingly, but this is a map derived from some of Arthur Merschat's work at the USGS, where he compiled a lot of data about different metamorphic zones. This has got nothing to do with timing. I'm not implying these are all the same age, because they're not. But you can see chlorite zones, CHL, kyanite zones, KY, etc. I'm going to concentrate on the zones that say KY or kyanite, sillimanite, and et cetera, right in the area of Alabama, because that's where the Alabama graphite belt is, so, which is shown here with this stipple pattern. So these are upper amphibolite facies, selimanite zone rocks for the most part. There is kyanite also. And what they look like in thin section, plain polarized light, you can see garnet crystals, these big roundish crystals, and we can see biotite, muscovite, et cetera. This, by the way, this is from drill core in one of the prospects from Westwater Resources in Alabama, the southern part of the Alabama graphite belt. And the dark material you see there is graphite, and then vanadium-rich muscovite is very common in these rocks, as was pointed out earlier. These are very interesting rocks. Now, by the way, I want to start out by saying that perhaps somewhat similar to places here in Sri Lanka, a lot of the graphite is actually concentrated in the weathered materials above this bedrock. So I'm showing you the bedrock because that's of interest to me in understanding how the graphite got there, but a lot of what might be mined is actually in the saprolite, where there's concentrated graphite in the weathered zone above this. But, so metamorphism, yeah, most of it is, the selimanite is often fiberlite or very fine-grained needles, in this case shown here within a muscovite crystal. And the drill core looks like this, and drill core is immensely valuable in Alabama because it's very difficult to see unweathered rock unless you drill it, unless you actually look at it carefully. The pink stuff you see in there is garnet, and that's not solid graphite, by the way, but there is graphite in this drill core. Now, I was very much interested in trying to understand exactly what conditions the flake graphite in these deposits was forming, and so I went after this with phase diagram modeling, which involved analyzing the rock for its bulk composition and then making a forward model of PT assemblages or assemblage stability with pressure and temperature. This is two examples. The details aren't really important, but the tan area there is the stability field of the peak metamorphic assemblage in these two rocks, which are from the same drill core right next to each other. So if you assume that they both crystallized under similar temperature pressure conditions, which seems very likely, of course, then we can overlap these assemblages and estimate the PT conditions for this rock, which come out at 650 to 690 degrees C, 6.7 to 7.5 kilobars, and they're right on the edge of the solidus, which is shown there in red. And some of the rocks in the Alabama belt, graphite belt, definitely did partially melt, and I believe that actually Liz Boland's done a lot of work on that. I have not, but she has some great samples where we see partial melting. So we know what the metamorphic conditions are in the graphite forming the graphite rocks. And we also know the timing, as was pointed out by John just a minute ago. I've done a lot of garnet, samarium, neodymium work in these rocks, and we can use a very similar type of theoretical approach to geochronology with samarium decay to neodymium. And we do it with isochrons, just like this. And so a garnet isochron from that drill core, same Westwater Resources rocks, we get 353 plus or minus 3. So as you can see, that's almost a direct overlap with what John presented a minute ago. And so these are for rocks in the drill core, but we also have another age nearby, which is, well, nearby being relative. It's not in Newfoundland, but it's almost 100 kilometers away, but it's upstrike along the same strike of these selimanite-bearing rocks, and it has a similar age of about 355. So we know the age. We also know the cooling ages of these rocks from argon 4039 in the drill core. And by the way, the vanadium muscovite is beautiful. There it is. Gorgeous green colors. This is not roscolite. It's not 17 weight percent vanadium. Most of this is only 2 to 5 weight percent vanadium, although I did not analyze the crystal that I did the argon work on. So these cooling ages are 347 and less. So they go down to 339 in this case and 342. So 337 to 347 are the cooling ages for argon 4039 in these rocks. And some of these are taken from very small grains, biotite, some of it's taken from muscovite, some of it's taken from pegmatite. They're all very similar. But the really interesting thing is that we can think about the textures of the graphite and then try to correlate this with the different ages, which not only are produced by the argon work and the peak garnet work, but also from what John has been doing with the rhenium osmium and the graphite. So if we look at these textures, there's disseminated graphite as shown here, which is essentially schistose layer parallel. And I would correlate that with the 355, circa 355 from the Garnet ages. And then there's also some layer graphite, which is also layer parallel. And I suspect there's been some mobility there to make these layers during peak metamorphism. And so I think that's probably also 355. You can see it. Now we also have cross-cutting veins of graphite, which is shown here along these brittle fractures. And I would estimate that these are probably post-peak as brittle deformation, perhaps around the age of the cooling, 340, given the argon ages. And here's some other examples of graphite textures in these rocks. Again, brittle fractures. This one also shows some folded graphite layers, which were probably the earlier phase. And then finally, we have some more brittle fractures here. And so we have a whole slew of different textures of the graphite, which I think we can correlate with our geochronology now. So in conclusion, I would say that the disseminated graphite crystallized during regional metamorphism, the flake graphite, and the bigger crystals, of course, were probably forming at 650, 690, maybe even in some cases 700 above the solidus, and around 7 kilobars pressure. So I would say that that's also when we had graphite or carbon mobility into these fold hinges that we see in the textures. And layers and lenses of schistosity parallel graphite, probably limited mobility, but some concentration, probably maybe even just centimeter scale mobility, not much more perhaps. And so in a general sense, I would argue that in this case, what we are looking at is metasediments rich in carbon with very limited mobility of that carbon and formation of this flake graphite. So in this case, I don't think we have to call on any large-scale mobility from long distances. And just to finalize what I've got to say is that I think we can correlate this really well with peak metamorphism. I also would say that it's really important to know the ages and the conditions, because if you go across a couple of faults within Alabama, you're looking at completely different ages, completely different histories. And so in an exploration standpoint, of course, we do need to know this kind of information about metamorphism and not just where the graphite is. If we want to find more, we've got to use all the tools at our disposal. So I will conclude with that, and thank you for your time.
Well, that was a wonderful presentation. Thank you very much, Professor Harold. Let's thank all our speakers for those engaging presentations. And we now invite all participants to proceed for the group photograph to PGI's Block C entrance, followed by lunch and networking.
With Boland, who's going to talk about investigations in the Alabama Graphite Vanadium Belt by the Geological Survey of Alabama. Welcome.
Good afternoon. So before I get started, I'd like to put things into a bit of perspective for you. So you've already seen a little bit about Alabama Graphite Belt already today, but graphite's actually present in more than just the graphite belt. It's present as amorphous, flake, and as very, very small discrete veins that get a little bit bigger than what Dr. Stowell described, but really only about 1 centimeter max. The Alabama Graphite Vanadium Belt contains the most of the flake graphite and vanadium-bearing mica in the state, and it's the largest reserves of flake graphite in the lower 48. And we have recently, at the survey and with our colleagues at the USGS, actually have expanded the belt into a subsection called the Expanded Graphite Belt, and I'll chat more about that in a little bit. Alabama is also home to a growing battery manufacturing industry, which is, of course, quite interested in lithium-ion battery graphite. And there's also a growing interest in mining the graphite in the state. It's been mined in the past, but has not been mined since about the 1950s. And as part of the Alabama Geological Survey's mission, it's our job to disseminate the information about the graphite belt to the industry and other stakeholders in the state. And as such, we've got multiple projects that are currently ongoing in the graphite belt. So you've already seen this map showing the Hank Williams 1978 geologic map of the entire Appalachians, and we're only looking at the very, very tail end, basically where the metamorphic rocks end at the coastal plain onlap. So these are Laurentian-derived sediments, the metasediments, that are deposited as late as about the Ordovician, although that's somewhat in flux. There's not a whole lot of information about that, but generally Ordovician in age, metamorphosed about 350 to 320 MA, and there are 6 graphitic units. These are interlayered with amphibolites and intruded by multiple suites of igneous rocks of various ages, and they're also bounded by multiple fault systems, many of which have experienced multiple episodes of activation and different directions of movement. And for the purposes of this talk, I want to make sure you're all aware that the graphite belt here is shown as the bright yellow. The greens and kind of teal colors, that's the expanded belt, but I'll show another map of those in just a minute. And here is that other map. So now that bright yellow is now red. The expanded belt is shown in yellow. And I'm going to refer to these as the historic belt, which was previously mined, as shown by those gray circles, and the expanded belt, which has not been previously mined. The areas of resurging interest by mining companies are shown by the stars. And this is what the historic production looked like. These were open pit mines with their own processing plants attached. The processing plants basically just did flotation on the graphite, separated it out, concentrated it, and shipped it elsewhere. And I want to point out the image on the lower right there. That's from the Ceylon mine, named for deposits in Sri Lanka, so a bit of a connection there. And the deposit there is quite amazing in its graphite concentration. So the mining stopped in about the 1950s. The belt was targeted primarily due to its high graphite content, that big beautiful flake graphite it has, and the softness of the rock. It's quite soft and weathered in Alabama, a bit similarly to here, makes it easier to process and crush. There's also a somewhat significant vanadium oxide percentage, about 1% or more, but I'll show some more recent numbers for that in just a few minutes. So the resurging interest, once again, I said that this is targeting the weathered rock. This is to supply graphite for the lithium-ion battery industry, as well as high-purity graphite for other applications. There has recently been completion of construction of a graphite processing plant in Kellyton, Alabama, where they convert flake graphite into spherulized graphite for the battery industry. The company that has done this is called Westwater Resources, and they do plan to begin mining in Alabama, maybe about 2028, depending on their time frame, in a mine that's 34 kilometers from the plant. So it's very close, relatively speaking, with highways and transportation corridors. And they've got 26 million tons of inferred mineral resource and 3.75 million tons of contained graphite. The Alabama graphite projects by the Alabama Geological Survey are shown as the blue boxes on here. Those are quadrangles, 7.5 quadrangle maps. Because of the resurging interest, we've started these projects and have finished the one on the lower left in the southwest, and are currently working in the 3 on the northeast. This is in partnership with the USGS Earth MRI program, which you don't know anything about. I'm happy to discuss, and I'm sure the other USGS colleagues in this room will be very happy to discuss the Earth MRI program with any of you. The focus areas are both on the historic and on the expanded belt, with the goals being to refine the geologic mapping of the graphite belt first and foremost. The only existing mapping in much of these areas is at the 1 to 250,000 scale, which is quite coarse. We would like a little bit better. And we would like to complement this mapping with geochemistry, and this is basically a broad brush approach to sample for the graphite belt for not only its graphite content, but also vanadium and any other critical minerals that may be present. Another big goal is to make all of this data publicly available. As I said before, this is the big push, is to just make this available so that industry and others can access it. Another big partnership with the USGS is airborne geophysical surveys. This is also with the Earth MRI program, and they have flown magnetic, radiometric, and electromagnetic flights over Alabama, as shown by these yellow and blue polygons. This is high quality. It refines existing geophysical data that has been flown in the past, but it was lower quality, and it helps refine traditional mapping. It also helps with better understanding of structures, which can help identify concentration zones for different mineral systems, including graphite, and look for those critical minerals. So here's an example. This is the electromagnetic survey over the Alabama Graphite Belt. Electromagnetics measures the conductivity of rocks, and graphite is very conductive. So on the map on the right, it shows blue zones. That's where all the graphite is. We like to call that blueite. Where it's yellow, that's where there's not a whole lot of graphite. And you can see, even in the graphite belt, it comes and goes quite a lot. It's not all graphitic within the graphite belt. There's some that don't have any. There's some units that have a lot. That's where mapping comes in. But it really helps to pinpoint the graphitic horizons within these lithologies and allows for better resource assessments. Another thing I want to point out on this map is the high graphite concentration in the expanded belt to the south, which was it was known, but it was not known to be this intense of a blue, so to speak, on this map prior to this flight. So this is a bit of an example of how you can use modern geophysics to help map, help refine existing maps and current mapping. So we're looking up here on the very upper right or northeast portion of the Alabama Graphite Belt in an area that's got amphibolite and graphitic schists and quartzites, as well as non-graphitic schists. This is a very structurally complex area, and the only published mapping is at the 1 to 250,000 scale. On this map, there are blue dots and there are yellow dots. The blue dots are where I observed amphibolite. The yellow dots are where I observed schist. Okay. The dashed lines are the 1 to 250,000 scale mapping, just for reference. And the field observations indicate a substantially different topology than what the state map shows. They does not follow the state map geology at all. The 1 to 250,000 scale map does not match what I see. So if I were to redraw, I might draw something like this for the contacts. In between the blue lines would be amphibolite. Outside would be schist. However, there's a lot of data gaps here. I can't go everywhere. Some places aren't accessible. Some places don't have any outcrop. So how do you fill in the gaps when things look like this? Covered in trees, a lot of pine straw, no outcrop at all, just dirt. Well, you can use geophysics, and this is an example of the potassium radiometric map. The black is low potassium, the yellows and oranges, that's higher potassium. So schist versus amphibolite shows up quite well here. And you can outline some of these, and it matches the field observations quite well, if you remember those blue lines I had on the prior map. And so this allows for contacts to be inferred in areas that you can't physically go. So you go from something like the 250,000 scale map on the left to a more refined map or more realistic map on the right. One more tidbit about data, though. Never underestimate the power of data preservation. Now, in the U.S., we have a National Geological and Geophysical Data Preservation Project that's also funded by the USGS to help states digitize, make available their old archive data. This involves both geologic maps, paper copies, and closets, basically, that have not seen the light of day in many years in some cases, as well as drill core and physical samples. So to throw in that example again of the same area I showed prior, we have found a geologic map published by workers from the Billiton Mining Company on a copper mine in this area. And their geologic map matches what we see quite well. It matches the geophysics, it matches what I've seen in the field, and we even have drill core from this area. So this just highlights how useful old data can be. So it's important to locate it, because we didn't know this existed, and use it, make it available, publish it, or at least reference it in a way that's meaningful. And with the addition of the drill core, we can also begin to get a sense of 3D interpretation of this geology. All right, so let's step back and look at the rocks for these belts. In the historic belt, the images on the right are all hand samples taken from there. They're highly graphitic in places with flakes up to 3 millimeters and up to 15% modal abundance, but most are 1 to 5. These are isolated flakes that are sometimes intergrown with mica. And the schists also contain muscovite, sericite, quartz, biotite, sillimanite, kyanite, garnet, and the occasional staurolite. In thin section, the flakes are quite pronounced. This is a typical thin section, no veins in this one, unlike what Dr. Stoll showed. Just large flakes that are moderately deformed in some places, but generally undeformed. The vanadium mica in the belt is very nice green, almost a spearmint color green, and it's also up to about 3 millimeter crystals, although it can also form up to 1 centimeter porphyroblast or clast, depending on interpretation of these rocks, kind of up for debate. Up to about 5% volume of the rock, and these, using laser ablation ICP-MS by my colleagues at USGS, Rebecca Stokes, we see up to 8,000 ppm vanadium, averages about 6,000, and up to 13,000% barium, averages about 10,000. So these are vanadium barium micas, which isn't too surprising. In contrast, the expanded belt is much finer grained. It's also variably graphitic, but it's mostly fine-grained schist and phyllite. Some lithologies have up to 25% graphite, but these are often restricted to layers that are centimeters thick, but it's quite amazing how much graphite are in these schists. There is vanadium mica present, but it's only been reported and not directly observed by us during the current project. Geochemically, we've got 300 samples of geochemical data. These are whole rock data analyses. Let me step back for a second. Carbon isotopic data on the graphite itself shows negative mid-20s to negative 15. So again, looking at an organic source. 300 geochemistry data for whole rock, both major and trace element data, show vanadium concentrations up to 2,000 ppm, which are unsurprisingly in the vanadium-bearing mica schists. Although I will point out the unit in red there that I have circled, that's in the expanded belt, and it also has excursions up to about the mid-1,000 ppm level as well. So that's an interesting thing that warrants more exploration on our part. And there's no correlation between the amount of graphite in the rock and the vanadium concentration in the rock, which is somewhat surprising. We were hoping for some kind of correlation because that would help with exploration, but oh well. We can also use this data to help infer something about the provenance. So the ternary has zircon, vanadium, and barium. They cluster, each unit clusters in certain areas. And we see similar trends in silica versus aluminum and silica versus zirconium over vanadium. So these are all just ways to look at the rocks in terms of their petrogenesis, maybe their depositional history, or maybe anoxic versus oxic conditions on when where they were deposited, as well as sediment composition. So much, much more work is needed on these. So the next steps for this, that's sort of where we're at right now with our survey work, is continue mapping and sampling this belt. We need to do a lot more 1 to 24,000 scale mapping and maybe even finer scale. Metamorphic grade and graphite crystallinity needs to be assessed at a broader scope than we currently have. And we need to better understand the viability of vanadium as a co-commodity. We also need to better understand the structure and tectonics of the area. That's where the geophysical data will come into play. And continue our data preservation efforts, because you never know what you will find in those closets. All right, and that's all I have, so thank you.
Thank you very much. We'll take 2 quick questions.
Thank you. So you mentioned that the vanadium content didn't correlate with the graphite. Would it be possible to measure, or do you think there could be a correlation in the speciation of vanadium? Like if you looked at reduced versus oxidized vanadium?
Short answer is maybe. But I would love to know. That'd be a good.
Yeah, just
good-
given that graphite is on the extreme side of reduction here.
Exactly. It'd be good to know that for sure. And maybe we should chat more about that, about how to pursue that.
Maybe I can comment a little bit from industry perspective. So it is extremely good that they are not correlated because vanadium is a very bad impurity for batteries and it needs to be removed, right? So I encourage you to find areas within the belt where concentration of vanadium naturally occurring is low and graphite concentration is high. And this is where you want to mine.
Yes, I agree 100%. As a caveat to that, the data I showed there was whole rock vanadium, so it wasn't vanadium in the graphite. So we don't know the vanadium content of the graphite for all of those samples.
Okay, I think we will have to move on. Thank you. Our next speaker is Jesse Mulsoff, and he's going to speak on the geologic framework of graphite deposits in the Ruby Range, southwest Montana.
Okay, well, while she pulls that up, I just want to say thank you for the opportunity to speak today. This is truly a great honor. Okay, yeah, so I'm a geologist with the Geologic Survey in Montana in the United States. And right now I'm serving as the program manager for the mapping division. So today I might be preaching to the choir, but I want to speak a little bit on the importance of geologic mapping to understanding ore deposits and such as graphite deposits in terms of providing a geo framework. And I'm going to give you an example from the Ruby Range, which was introduced earlier by George's excellent talk. Okay, so in this photo, I'm standing in the Ruby Range. That's my field vehicle that I live in for 3 to 4 months of the year. And I'm parked or camped on Precambrian basement rocks that are mainly Archean to Paleoproterozoic in age. And the crystal graphite mine would be just out of photo left there, kind of on the next ridge over or so. Okay. So the Montana Bureau of Mines and Geology is a department within in the university system, the Montana Tech University in Butte, Montana, which is shown in this aerial drone photo. And we have wonderful geology right out our back door. We're located in Butte, Montana, which is in the northern Rocky Mountains, near the Canadian border, kind of. And the reason I included this photo is if there are any Sri Lankans in the audience that are mid-career and are interested in a scientific exchange, maybe with the Fulbright, I don't know, come talk to me, because I'd be very interested in that. Okay, so the core mission of the Bureau is we serve as sort of the geoscience data center for the state. Okay, so why geologic mapping? Well, geologic maps show the composition, spatial relationships, and age of rocks and structures at or near the surface of the Earth. And they have a wide range of applications from geohazards to natural resources, such as graphite deposits or even groundwater. And they're also really useful for just basic geoscience research. Okay, I don't have time to go into the details of this, but I encourage you all to check out this cost benefit analysis that was recently done by Berg and Falds, who's at the Nevada Bureau of Mines and Geology. And their conservative cost benefit estimate was that a map's value can be up to 10 times the cost that it took to make that map, with a more liberal estimate being up to 35 times the cost. So we get a tremendous return on our investment in geologic mapping. Okay, and geologic maps are critical to understanding mineral systems, like George described earlier in his talk. And so these mineral assessments require high-resolution geologic and geophysical data, and we take that data and integrate it to create mineral potential maps, for example. So this is a case from Alaska where they've integrated multiple data sets, including geologic maps, geochronology data, mineral occurrence data, and geophysical data to make a mineral potential map. And I just want to point out that the geologic maps are the proverbial bedrock for these assessments. And that includes, the surface geology, the structure. A lot of times we're mapping the structural geology along with the surface geology. And I also want to point out that age dating is really important for these studies too. Okay, so most of the mapping we do is supported by the USGS National Cooperative Mapping Program. We participate in the state map prong of that. This program was signed into law as the National Geologic Mapping Act in 1992 and has been reauthorized several times. And the act recognizes that geologic maps are the primary database for virtually all applied and basic earth science investigations. Okay, so at Montana, we have two long-term sort of state map goals. The first being to create uniform geologic map coverage of the entire state. That figure on the lower left there is a progress map towards that goal. It's a little busy, but all the colors show what we've completed, and the white boxes are what we have left. So that's all in the northwest part of the state. All of our mapping is guided by societal justifications, again, including things like hazards and natural resources. Okay, so where do we have graphite deposits in the U.S.? This is a map I pulled off the USGS website showing occurrences with 1,000 metric tons, containing 1,000 metric tons of graphite that's either there or been mined. And the first thing I want to point out is that there's not that many, right? You can hardly see any dots on that map. But there is one occurrence in Montana, that crystal graphite mine. Let's see if I can point it out. It's that small dot there. And this mine's located in the Ruby Mountains, again, of southwest Montana. And it historically produced about 2,400 tons of graphite. It was discovered in the late 1800s and was mined till about the mid-1950s. And that graphite, again, is hosted in Precambrian metamorphic rocks and probably has a polyphase sort of mineralization history associated with it. Okay, so this is a map from the USGS database showing where we have Precambrian geology exposed at the surface. And kind of like the graphite map, you can see that it makes up a very small percentage of the geology exposed at the surface anyway in the US. Presumably large parts of the continent are underlain by Precambrian rocks that are just not exposed. So if we zoom into Montana, we see that the Ruby Range is plots in those sort of magentas and pinks you can see there that are mostly Archean to Paleoproterozoic in age. And again, these are crystalline basement rocks. This area is part of what we think is part of the Wyoming craton, which is this ancient cratonic crustal block, if you will. It could be up to 3.6 billion years old. And the Ruby Range is actually really close to this sort of nexus with its neighboring terrains, including the Medicine Hat Block, Selway, and Grouse Creek blocks, according to these authors anyway. So tectonically, it's a complicated area. And then on the right figure there, the Wyoming craton itself has been mapped or described as two sort of separate lithotectonic terrains, the Beartooth Bighorn Magmatic Zone, and then this Montana metasedimentary terrain that the Ruby Range is located within. Okay, so zooming in at the Ruby Range, the local geologic setting of the Ruby Range is quite complex, as you can see by this smattering of colors on the map on the left. This is like a 5-day lecture all on its own, and I've actually mapped a lot of the geology in this area, everything from active faults to Cenozoic intrusions and volcanic deposits, and of course the Precambrian basement rocks of the Ruby Range. But if we look at the Ruby Range itself, well, first off, how did the first question you want to ask is, how did these rocks get to the surface? These are high-grade rocks, again, Precambrian crystalline basement up to granulite facies. How did these deep-seated rocks get to the surface? I don't think we fully understand that, but we've been collecting thermochron data that suggests these rocks were brought rapidly, or cooled rapidly in the Cretaceous, so that could explain part of their exhumation history. But more or less, the Ruby Range is underlain by those Precambrian rocks, and then the north part of the range, you can kind of see those purple-blue colors. Those are Paleozoic rocks for the most part, unconformably resting on the Ruby Range, and then all the browns are unconsolidated tertiary sediments and quaternary sediments surrounding the range. Okay, so we mapped the Ruby Range as this Dillon 30 by 60, as part of our Dillon 30 by 60 project, 100,000 scale map. We did all the mapping at 1 to 24K scale, which are all those little tiny boxes on the figure on the left. All the colored boxes show what we actually mapped. The pink boxes are the 24K maps that we mapped in the Ruby Range ourselves. The gray boxes are EdMap projects. And this past year, each individual 24K map we've published as a standalone product. This is an example here, the Christensen Ranch. You can see it has all the elements you'd expect in a geologic map, cross sections, a fair amount of detailed mapping, some analytical work. And I actually have this map here along with some other 24Ks that I encourage you to come check out at the poster session. In this past year, I've been bringing all those maps together and simplifying them into a 100K scale map that covers the entire Ruby Range. This is a crop of that 100K compilation, 100,000 scale compilation. It's going to quickly walk you through the geology of the basement rocks. So traditionally, they've been described as three metamorphic suites, including the Elk Gulch, Dillon Gneiss, and Christensen Ranch. On the right, I have a lithostratigraphic column showing kind of the general pseudostratigraphy. The Elk Gulch is thought to be the deepest metamorphic unit, maybe the oldest. It's mostly composed of these more mafic gneisses with some schist. Above that, we have the Dillon Gneiss, which is dominated by quartzofeldspathic gneiss for the most part, with some amphibolite, I should say. And as we go to the top of this section, we have this Christensen Ranch metasedimentary suite that has a lot of metasediments, as the name implies, including marble, calc-silicate, schist, quartzite, amphibole. There are banded iron, and there is some leucogneiss in there as well. And there is amphibolite all the way through all three of these units, and then in turn, they're all cut by these younger diabase dikes and pegmatites that are maybe 1.7 GA in age. I'll come back and talk about the age of the various metamorphic suites here in a minute. Okay, so this is what these look like in the field. They can be very heterogeneous and it's hard to capture their nature all in one photograph, but the Elk Gulch tends to form these dark kind of weathering gneissic outcrops, and one of the key signatures of this unit is that it can be very migmatic, which is kind of hard to see in that top photo, but there's some migmatite in there. The Dillon Gneiss tends to form these lighter colored quartzofeldspathic outcrops that form the kind of the rocky spine of the Ruby Range, and they can be banded locally. And in the Christensen Ranch on the photo on the right there, you can see the marbles in the upper photo, some banded iron in the lower photo. Sorry, I have to rocket through this. We've done a lot of geochronology on these rocks. We do all our geochronology at the lab at UCSB. We use the LAICPMS technique because as mappers, we're dating a whole variety of rock types of all different ages, and this technique is really versatile for us and cost effective, and we don't mind going to Santa Barbara once a year to run the instrument. Okay, so all in all, so far we've analyzed about 53 samples. Sorry, you can't really see, I plotted them on the map there, but they're really hard to see. But anyway, we have a pretty good spatial distribution of our sampling. On the right, you can see some examples of our results, and long story short, they're complicated. A lot of times we have lead loss and discordance, and even the concordant ages can have a wide distribution. So they're pretty hard to interpret, but what I did for this talk is I took all the data from all 53 samples, applied a really strong discordance filter, and you can actually see some pretty interesting trends here. So on the left is the tectonomagmatic history that's been put together for the Ruby Range from previous geochronology and studies in the Ruby Range and surrounding ranges. Excuse me. On the right, I have a distribution plot of all of our, every single zircon that we analyzed that's less than 10% discordant. And then on the right, I have their corresponding thorium uranium ratios plotted. So we have a small peak at about 3.5 GA. So the protoliths of these rocks could be as old as that. And those zircons, if you look at the thorium helium data, which ratio, which tells you whether the zircon's igneous or metamorphic. Not always, but it's kind of a rough ballpark indicator. You can see those look mostly igneous. Okay, I'm gonna have to rocket through this. We have a peak at 3.3 GA. Those also look mostly igneous. There's some scatter in there. We have another really strong peak at 2.7 GA. And again, those mostly look to be igneous zircon. And then things get interesting at about 2.45 GA, which is the beaver heterogeny. And you can see like our trends in the thorium uranium data shift dramatically to the left there into metamorphic territory. And then similarly, we have the big sky orogeny at 1.7-ish GA, and again, those look to be metamorphic. I'm just going to skip over this, but you can tease out the data, break it out by map unit, and each map unit seems to have its own sort of age signature. Like Alabama, these rocks have seen a lot of deformation. This could, again, be like a 5-day lecture all on its own, but I'll just say that for the most part, there's a really penetrative foliation through all 3 units. You can see on the stereo plots there. It's mostly dipping to the northwest, but locally folded. And what I did on this map is I mapped in a big aniform that we're not showing on the 100K map, but I do think that the Elk Gulch is a core to this sort of mountain scale isoclinal aniform that's verging to the southeast in its current geometry anyway. There's a lot of late Cretaceous overprinting. I'll just kind of skip over that, and as well as extensional faulting. This is a seismically active area. There's been extensional through the Cenozoic that's been pulling apart those older shortening structures. Okay, so I'll just wrap up with some correlations to George's recent work where he was able to date titanite and diopsid graphite alteration and got an age of about 1.77 GA. And that, based with some of those older ages on the marbles, he I guess, proposed, he'll tell me if I get this right, but proposed at least a polyphase, or like two-stage growth with flake graphite at 2.45 during GA during the Beaverhead orogeny, and then vein mineralization of graphite during the Big Sky orogeny. And that lines up, as you can see, lines up pretty well with our geochronology data. A recent tech student, Mickey Taylor, she identified, in addition to that sort of peak metamorphism related to the Big Sky orogeny, she identified some low temperature minerals intergrown with graphite and proposed some retrograde metamorphism following that Big Sky event, but it doesn't have an age for it. Okay, and with that, I'll wrap up and take any questions. I guess my main conclusion is geologic mapping is really important.
Thank you. We're going to have to defer questions and move forward, but thank you very much. Our next speaker is Brent Elliott, and he's going to speak about legacy graphite mining in the Central Texas Graphite District and new mine development impact on U.S. domestic production.
All right, so before the slides get up there on the screen, so I'm Brent Elliott. I'm an economic geologist and research professor at the University of Texas at Austin with the Bureau of Economic Geology. And that's the State Geological Survey of Texas. Little that people know that we are the largest state survey in the United States. We have about 250 scientists and engineers that work there at the university. Everybody knows that Texas is an oil and gas state, right? Known for cowboys and ranchers and those kind of things. But oil and gas, for the most part. Don't know probably that Texas is also a mining state, right? We produce more mine material, more mine revenue than any other state, typically in the top 5, and it's all industrial minerals, right? All sand and gravel, limestone, crushed rock, and that kind of thing. So this project probably wouldn't have been possible without the funding opportunities, which is kind of an important aspect for all of these talks probably, is that without funding, right, we wouldn't be able to do this important work. And a lot of this work that we did here, this is all prior to the Southwestern Graphite operation kind of reinventing itself and restarting in Central Texas. It was all funded by the National Data Preservation Project from the USGS, as well as the Mine Waste Project for Earth MRI, the Earth Mapping Research Initiative, and then partly by Department of Energy, CORE-CM, which was the Carbon Ore Rare Earth Critical Mineral Project, and then also the state put in some money with the State of Texas Advanced Resource Recovery Fund, right? So a lot of different funds and buckets of money goes into kind of the resource assessments and resource research that we do within the state. And of course, our colleague here, Shelby Short, is going to give a talk here about modeling in the not too distant future. And she's done a lot of work on this in preparation for this conference and this topic in general in previous conferences. And Emeritus Professor Rich Kyle, who's not here, but he's done a lot of work on this area historically. Okay, it's a tectonic reconstruction of the central Texas. Do we have a laser pointer? Right, so you see Texas, the Llano uplift area where...
I think you can use the pointer on the screen.
Oh, yeah. All right, smack in the heart of Texas is our largest Precambrian exposure in the state. And that's where our new graphite district, or we call it the Central Texas Graphite District, in not just one locality, hopefully, in the near future. All right, all of this was forming during the schists and gneisses were formed during the Greenville orogeny at about 1.23 to 1.27 billion years. And then following the extension of that orogeny, we have the input of a bunch of Precambrian granites at about 1.03 billion years that forms Talon Mountain granite. And these are all within plate, basically extensional or transtensional granites that form in the center of Texas. Beyond that, there are a few Precambrian exposures out to the west part of the state, but for the most part, this is our exposures. And pretty much the only graphite occurrences that are in the state of Texas. Here, an idea of what it looks like. Most of this is either gneiss or schist along the flanks of the Precambrian uplift. You know, you have a bunch of Cambrian Ordovician sands. You know, these basal sands that are on this kind of brownish colors around the outside. There's a number of graphite occurrences that are all across this area, kind of on the edges of that granite, which is the center of this area. But you have the schists and gneisses that kind of form this kind of darker pink color throughout the area. I should note that we also are, I guess, benefiting from the Earth MRI project, kind of like what Liz was talking about in Alabama. There's a plan to do an aeromagnetic and radiometric survey across this entire area, and then follow that up with an EM survey over the kind of the hot spots or the areas that are probably going to be showing where graphite occurrences or other kinds of deposits that may benefit from that kind of geophysics. And that's all courtesy of the USGS and the geophysical needs in that program, which is a huge boon for a lot of state surveys in a lot of areas across the U.S. Again, money and incentivizing mining and incentivizing kind of resource assessments and characterization is a vital component to development of new resources or developing of old resources in a new way. To give you an idea of kind of what those rocks look like, you can see these gneisses and schists. Like I said, this is the Paxidal schist, where predominantly our graphite belt, and specifically it's the Honey Creek Formation. Within that, I think someone had mentioned about they're usually a strata that's specific to the graphite formation. So the Honey Creek within the Paxidal schist in Texas is where it's at. It's all syngenetic. It's not epigenetic, right? So presumably the age of the Paxidal schist, although it'd be nice to get some dates on that as well. So this is an example of the historic graphite mining. That building, you can go out to the current location now and see some of the structures and the new development. But that's kind of what it looked like before it was burned down a couple of times. And I think someone had mentioned Joseph Dixon. Well, he was also involved with this, with the American, with his company there. So in 1913, the deposit was discovered. Production began in 1918 and occurred until 1979. So a lot of the production was between 1961 and 1979, but over, I think the estimate was 1.6 million tons and about 5.2% flake graphite, and about 75,000 tons of production over that time period. So if you look at 1961 to 1979, it averaged probably about a little over 1,900 tons, or 1,925 tons per year during that 10-year period. So we're looking at the tailings because at this point in time we've been called out by the landowner basically to see what we could do with his tailings material it was producing a little AMD, some acid mine drainage that was causing some problems in one of the streams there. And he was using that sand material for soil amendment. And so we had taken a bunch of samples for characterizing it. And this is before they decided to kind of open up and expand the previous mine area into a couple of new mines. And so we were looking at the graphite content, flake size distribution, any way to liberate that material, and then look at all of the mineral associations and then the flake shape morphology. Using things like combustion infrared detection, right, C fractionation, and then a lot of SEM imaging with EDS so that we could get an idea of what the character and quantity and quality of that material was. Overall, probably about a little bit less than 3% on some of the samples for the graphitic carbon content. Most of that sample size was between 219 microns and 17 microns, with the 50th percentile about 79 microns in size. Those that kind of elongate shapes. You look at the kind of the modal mineralogy. Of course, most of it, that sand tailings material is going to be quartz, plagioclase, K-feldspar, along with some amphibole, pyroxene, garnet, and biotite. We got quite a bit of graphitic clay, up to about 12%. Typically, along with some iron oxide hydroxides, inclinochlor, sulfate, and silicate aggregates. Has some jarosite mixed in there, and only about 2% graphite within that tailings material. Overall, it's about 2,000 tons of graphite. It was kind of the assessment of what still exists there in that material if it wanted to be mined again, along with some other added value products like ilmenite, titanium oxides, both rutile and ilmenite, and then the possibility of zircon and monazite, for heavy mineral separations if we wanted to add a circuit for that in there as well. Which, why not? If you're going to go ahead and sieve everything out and sort it, might as well get some other added benefit from it. Particle mapping, kind of looks like this. You can see a lot of the occlusions within the graphite material. You see the long elongate shapes of the graphite. See what the quartz grains look like with the plagioclase, and with the sorted, kind of the greens and blues for the micas and the amphiboles. The pinks and the light pinks and dark pinks being the other tetrasilicates like the feldspars and quartz. Imaging, if you look at the graphites usually associated with biotite, you see a bunch of high sulfur clays and graphitic clays that are mixed in there within it, along with the quartz, typical morphology of quartz mixed in with it. All right, typical zircons, an association along with the monazite we see in the SEM imaging. Normally large quartz grains like that with graphite mixed in. I think the important part, besides just looking at kind of the characters and qualities of graphite, if we were to kind of bring this mine kind of back on, and that's the plan, right? That they're developing it now, they're doing drilling, they've flown their own EM survey, so it looks like it's going to move ahead with production. If we look outside of the synthetic materials coming from China at about 400,000 tons on a global scale of production, the U.S. imports 71,000 tons, or about 18% of global production, right? Typically one of the higher ranking countries. So if they produced at least the new mining operation, Southwestern Graphite, if it produced 37,000 tons on average, or about the same production it had done historically, that would just move the needle a little bit. It wouldn't even be a little bit. We'd have to do a lot of production at one site or a lot of production at multiple sites in order to offset the 34% of material that we import still from China. So I think it's important to kind of point out that even if we have domestic supplies that are coming online, there's still a lot of room for other material from other places that could facilitate that need, outside of the reliance we have on the Chinese graphite material that comes in. So there's a lot of opportunity. I think that's probably the main point. All right, opportunity is there if people want to take advantage of it. All right, in conclusion, I'm probably way ahead of time, but past production history and resource estimates from the previous mine and then the expansion of 2 other sites at that same site, along with all the other sites around Central Texas, seem to be optimistic for new production, especially with all the new added information that we're expecting to get from the geophysical surveys. We see, the flake graphite's going to be good enough, I would think, for battery development if people want to take advantage of that. And I think even though the production is probably expected to be somewhere around 3% of the U.S. needs as a domestic source, like I said, there's a lot of opportunity for foreign materials that probably aren't Chinese materials moving forward. If anyone has any questions, I can take those.
Thank you very much. Given your very efficient talk, we will take a couple questions.
Is there a price point at which it makes sense to mine and under which it does not make sense to mine?
If you're making money.
That's what I'm asking.
Yeah.
What's that price point?
Well, it depends on your operation costs. It depends on everything that goes into it and whether or not you're actually going to make money as the operation. I mean, ideally, you're answering to your investors, right, or the people who, that you report to for the development of the mine. So, I mean, that's all it comes down to is if it's not economical, it's not going to happen. Mm-hmm. Yeah.
Patrick, it's $700 per ton.
He's got the answer.
All right. But, you're not counting Sri Lankan graphite, right? That's a separate story.
Right.
I'll ask him next All right. So, Brent, are you aware of any corporations which are doing exploration in Texas?
Yeah, there have been reports of some companies, but Peradeniya, one of the sponsors for this conference, they're the ones that are developing or redeveloping the Southwestern Graphite Mine. We looked at a lot of, for the National Geological and Geophysical Data Preservation Project, we initially went out to the landowner, and he gave us a lot of boxes, file boxes full of material, and that was everything from notes from human resources to the accounting, it was just a whole lot of paperwork. And we used that fund, that the USGS provides to archive all of that material and look at it. And it had data basically on all of the production and all the economics of it from historic data. And so, I think they have a lot of information, and like I said, they've flown their own EM survey, and they're going to start drilling to kind of prove up that resource. And so I think they're the main ones right now. There's probably others, though.
Thank you very much. I'm going to introduce our last speaker of this session. Hamish Fraser is going to speak to us now about Sri Lanka, from theory to discovery, the Rides Ganja success story.
Okay, good afternoon. I'm Hamish Fraser. I'm the Geology Manager at Margosa Graphite. I want to open today's talk with a quote from one of our industry leaders, Lucas Lundin. Success in the resource business takes 3 things. First, risk-taking. Second, you've got to be a giant optimist. And third, you have to be willing to go out there and do it. I'm here today because we, Margosa, went out and did it. The lawyers have told me we need to include this slide. It notes this presentation is not investment advice and covers the inherent risks for forward-looking statements. Now let's start talking about Peradeniya. The best indication of success and forward success is past success. It's the team that's all important. This team has been a cohesive unit since 2017. We've done it before, not just in Sri Lanka, but globally, across construction, processing, and the entire exploration life cycle. Okay, so what is exploration? What is exploration success? Is it finding an outcrop? That photo up in the top left there is the first look into Peradeniya. Is it getting a drill intercept? That's one of our first major graphite intercepts at Peradeniya, which gave us the positive reinforcement to keep going. But I prefer to view exploration success as it is defined by the JORC code, as discovering an economic occurrence of a solid material of economic interest in or on the Earth's crust in such form, grade or quality and quantity that there are reasonable prospects of economic extraction. So Sri Lankan graphite. There are over 3,000 reported graphite workings in Sri Lanka. Why did 2,997 of them stop working? Was it the geology, engineering issues, market? My old professor used to say exploration is like looking for a black cat on a black night that may or may not exist. To find an economic project, you have to be systematic, professional approach, I guess similar to looking for that black cat. This triangle represents the probability of finding a world-class deposit. You start with hundreds and thousands of prospects and spend a lot of money to find the one actual mine. The odds of a world-class deposit are approximately 1 in 1,000. I'll put some references up there if you're interested later. There are plenty of occurrences in Sri Lanka, but it takes time, rigour and money to sort the mineral occurrences from the mineral deposits like we have at Peradeniya. The world production of graphite was about 1.8 million tonnes in 2025. Sri Lanka's entire production, 3,200 tonnes, would be consumed by one new Tesla plant in about 10 days. Sri Lankan graphite is too valuable to be restricted to simple battery and graphene discussions as we've done in the past. We're looking at new horizons for specialty products. Demand is outstripping supply. The world's demand for Sri Lankan graphite is unknown due to the limited resources. In 200 years, Sri Lanka has exported roughly 1.5 million metric tonnes of graphite. We are all here to increase the graphite production. To do this, we are reporting to international codes, gaining industry trust with excessive verification processes we are undertaking. This diagram is the roadmap. It has showed us we have moved from mineral occurrence to exploration target to inferred and indicated resources. We are currently working on the modifying factors of environment and social and moving towards having an ore reserve. Margosa operates under the Crisco umbrella that represents organisations responsible for over 80% of the world's capital. Our reporting follows the JORC code and is guided by the ASX listing rules. This is the global standard for integrity and provides the transparency that the international investment market requires to move forward. Our code is built on trust, transparency, materiality and competence. So, in 2017, we recognised a critical bottleneck. The drilling wasn't delivering the required depth or recovery to define a world-class resource. So we imported an MD600 in the bottom corner there, and later an LT140 up in the top, to build our own fleet of drill rigs. We brought in an expertise, pairing an expatriate trainer with a local team to develop a specialised crew of drillers and offsiders. In parallel, we built intellectual infrastructure. We implemented the JORC 2012 code as our baseline and trained our geologists on its reporting requirements. We don't use Excel. It's not a database. We use Plexar. It's a geological data management trusted by international major companies like BHP and Whitehaven and some of the other giants in the resource industry. It provides security data, governance system and a single source of truth for every metre we drill, backed by the data security and backup systems. Independence is everything. Measure Group has been involved with Margosa since 2017, undertaking site audits, resource statements and feasibility studies. They're an internationally recognised company who work for the likes of Glencore, Rio Tinto and BHP. This gives another level of confidence to potential offtake partners and financial institutions. Having such a respected company sign off on our reports is really, really helpful. So, what have we done? We've drilled over 20,000 metres on 6 targets. We've focused heavily on Peradeniya with the goal of entering production. Having one project in production enables us to provide confidence to offtake partners and financial backers that there are markets and we can create more demand for the graphite. This in turn will help fund the exploration of other projects. We've also been looking into the long term with providing core to the University of Peradeniya to help them train the next generation of geologists. So our resource, what have we done? In February 2025, we updated our resource to 2.55 million tonnes at 78.19% TGC. That is 1.99 million tonnes of contained graphite. You can see from the 2020 and 2025 that we've been slowly increasing the size of our resource with systematic exploration. I'll touch very briefly on this cross-section. You can see the scale in the bottom right-hand corner of it. That's 100 metres, sorry. The vertical is about 300 metres. The cross-section line is through the yellow bit there in the middle with the grey, and we're looking north. You'll see all of our drill holes are angle drilled. This is so we can orientate all of our core and get orientation of all the veins. So we've also drilled perpendicular to the veins so we get the true thickness. In our model, there's over 110 graphite veins we've modelled. It takes, in our industry, 10 to 15 years minimum to discover a tier 1 mine, another 5 to 10 years to bring it to production. We're close to those numbers, having started work in Sri Lanka in 2012. When we started working in Sri Lanka, we were exploring for the elephant room. I'm going to pronounce this wrong, please forgive me. Ali Ilama, massive graphite veins. We soon discovered that there was another opportunity to mine significant quantities of graphite. We'd have to target thinner veins that were located closer together, utilising modern-day mining methods. The change in mining ideology enabled us to identify more areas of potential. Our studies have been detailed and time-consuming, but we have had to take the studies to the next level to give ourselves confidence before we progress in the project. The image here shows the proposed production on the 2nd of February 2032, so we can give an offtake partners confidence that we can deliver product. We anticipate that production levels will increase when we open up more mining opportunities, both at Peradeniya area and regionally. So the take-home message is simple. We got out there and we did the work. We completed geophysical programs, we drilled 20,000 plus metres, and we delivered independently compiled resources of 2.5 million tonnes at 78% TGC. This is in accordance with International Code of JORC. This amount of graphite is more graphite than we have found has been exported from Sri Lanka historically. We have a portfolio of projects that we're ready to take to the next step. We're moving the more prospective projects up the triangle and cutting the projects that don't stack up. Please feel free to come and ask any of my team any questions. And thank you for the opportunity to present here tonight.
Thank you very much, Hamish. It's wonderful to hear about all of the different things that go into finally production, which we hope that we soon.
Hopefully very soon.
Wonderful. So if there are any questions now, please.
At the
Yes.
back, yeah. We use geophysics, we use EM surveys, but as which was mentioned earlier on today, there's a lot of false positives with EM surveys, so you've got to get out there and drill the holes to really find the targets.
You mentioned that the graphite is too good for batteries and graphene what is your major target market?
There's a whole new world of markets opening up at the moment. You can, the whole synthetic market, this graphite is getting up to that level where we can offset synthetic. There's also all sorts of new space, medical and other avenues that can be explored.
Okay, thank you very much.
Okay, good afternoon, ladies and gentlemen. It is my great pleasure to warmly welcome you all to the Practitioners Forum of the United States Sri Lanka Graphite Summit 2026. This session is an initiative of the National Science Foundation of Sri Lanka in collaboration with the Department of Geology, University of Peradeniya, aiming at bridging the gap between research, industry, and policy of the graphite sector. The Practitioners Forum serves as a dynamic platform that brings together researchers, industry leaders, investors, and policymakers to foster collaboration and advance Sri Lanka's role in the global graphite value chain. This session will be conducted under 3 key themes: recent advances in graphite research, industry needs and market perspectives related to graphite, and policy and regulatory framework related to graphite. To officially commence this forum, it is my honor to invite Dr. J.G. Shantasiri, the Additional Director of the National Science Foundation Sri Lanka, to deliver the welcome and opening remarks. So over to you, sir.
Thank you. I am given 5 minutes. Yes. Okay. Good afternoon. And on behalf of the National Science Foundation and the Director General, I extend a warm welcome to all the dignitaries, to mention the Executive Director, the US and Sri Lanka Fulbright Commission, and dignitaries from the US Embassy to Sri Lanka and US delegation comprised academia and industry, and of course distinguished invitees from Peradeniya University, high profile professors and galaxy of expertise in the graphite field. Of course, from the National Science Foundation point of view, as you see, the main theme is advance in the science and technology in the natural graphite. This session almost focused towards the Practitioners Forum, where the National Science Foundation Sri Lanka is the premier organization, national level organization to foster the science and technology innovation in Sri Lanka. Our institution genesis goes to way back in 1968 as the National Science Council, which midway transformed into Natural Resources, Energy and Science Authority, which was transformed into the National Science Foundation by 1994. Our mandate, key mandate of the National Science Foundation is to foster, facilitate knowledge creation process, funding research and development, basic as well as applied, and of course capacity building, nurturing our young researchers as well as senior researchers, plus nurturing and advancing the research and development infrastructure. We have a spectrum of grant schemes to foster the innovation ecosystem in the country. So as per the national perspective, being the national and the government organization, we have to be aligned with the government priorities. As per the addressing the government high priority national concerns, apart from the knowledge creation process, we have more focus towards the application side, where we are expected to propel R&D output from benchtop to furtherance transcending giving solutions. If you see the current development, national development policy framework, there are certain priorities where it highlights and underlines, like scientific solutions to society, no one left behind, R&D commercialization and production economy, social well-being and the sustainability. So accordingly, of course, transcending R&D output, tech development, even scale up and startups. For your knowledge, I will highlight only few grant schemes. My research head also there, he will also little bit explain. We have 3 key grant schemes to propel R&D output towards the commercialization. One is the technology development grant scheme, where if the researchers are given, they have come up with R&D output having commercial potential, you could go through the process beyond the output for tech development and scale up, even commercial level, technology readiness level enhancement. If any researcher come up with technology ready product out of his R&D finding, we have a grant scheme for a startup, for a 1-year startup just to kick off the startup until he get the confidence for venture capital funding or the angel funding. So and also for the international audience, I would highlight, we have a specific grant scheme where international collaborative research program, where Sri Lankan research teams shall counterpart or the team up with any other country, US research team, and they can devise a joint proposal and ask for a funding. For Sri Lanka component will fund by the Sri Lankan government, of course National Science Foundation, while the counterpart research component is expected to funded by the respective country. So therefore, please during the discussions think on that line, and because today's practitioners forum is expected to discuss and deliberate on way forward, especially how your research will bring into the practice. Of course, I am sure this audience is the think tank or the cream of the triple helix model, where industry, academia and government all are in one room. So discussion flow is provided, facilitated, thereby I presume I invite, my humble request is always try your best to crystallize your idea, so that without restricting into a discussion, where I reiterate this morning opening remarks by Professor Kusali Gamage also, how trying to transform your recommendations into real partnerships, long-term R&D collaborations, and final product and process innovations, creating the wealth and social benefit. So that's the key message. And of course, as a layman, I'm not geologist. I little bit got an AI assisted to. I asked for the to scan leading Scopus, Taylor and Francis, and Springer Nature to summarize what are the cutting edge trends in graphite. They highlighted, in addition to this morning, and so that it highlights, summarize. Of course, as a proxy, there are some certain other directions as well, because Sri Lankan graphite and graphene applications are apart from the energy storage solutions, EV, it has the potential like energy dissipation applications, like even moderated nuclear reactor applications. Now with the AI and data science, it comes with the huge data center facilities where heat generation is a significant problem where you have to tackle. So now researchers are looking for energy dissipation solutions out of graphite. And also graphite has a lateral thermal conductivity over copper significant levels. So therefore also graphite has been researching on thermal conductivity applications and heat sinking applications. So I just want to spark your mind as a proxy and think beyond the application side. And also geological mapping is highlighted now with the AI and advanced hyperspectral banding blend has been deploying, researching, so that before going into the cumbersome process and costly process, they are assisting in easy, cost-effective mapping, geological mapping. So therefore, I see without boundaries, ample opportunities in the global market sphere. So therefore, being the National Science Foundation, we are ready to, I am sure our Board of Management will continue to support for promising proposals, projects, especially bringing practical solutions to the industry. So key messages, I am sure that these 2 days discussions and dialogues and partnerships established, I am sure solution will not give overnight, but please keep your partnerships long term and continuous dialogue. Definitely National Science Foundation will continue to support or facilitate to keep the ball rolling in partnership with the Fulbright Commission and the University of Peradeniya and other stakeholders, of course. So therefore, my humble request is to keep the ball rolling. NSF will facilitate and support whatever our way. So that's all as the key message. And especially, last not least, I want to acknowledge and recognize, sincerely appreciate the key role and untiring effort made by Professor Kusali Gamage, Fulbright Commissioner and Executive Director, and the US Sri Lanka Fulbright Commission team, Peradeniya University Director, International Research Relations Office, and of course my team, Ms. Tilina Kandanamulla, the Senior Scientific Officer, International Affairs Division of the National Science Foundation. Your untiring effort made today's event a success. Of course, thank you very much for your patience.
Thank you very much, sir. We now move to our first session under the theme Recent Advances in Graphite Research. Our first speaker of the session is Engineer Mahesh Disanayake, the head of the research division at the National Science Foundation, Sri Lanka. He will present an overview of recent advances in graphite research in Sri Lanka.
Hi everyone, very good afternoon to all. As our additional director mentioned, National Science Foundation is a main funding body in the country. So other than National Science Foundation, there are National Research Council and also Sri Lanka Council for Agriculture, Research Policy. They are also government funding organization. So they are also funding in this sector, uplift the research and innovation in the country. Especially in National Science Foundation, we promote the progressive advancement of the science, technology and innovation ecosystem to ensure well-being of the citizen of Sri Lanka. So that's why actually we are here to collaborate with Graphite Summit 2026 because as per our mandate 1, it says that initiate, facilitate and support basic and applied scientific research by universities, science and technology institutions and scientists with the view to developing and natural resources of Sri Lanka. So that include mineral resources also, that include graphite. So graphite is one of our research area under the National Science Foundation research thematic areas. So just like gems, that is very famous mineral from Sri Lanka. Graphite also very much famous from Sri Lanka, and it contributes to our economy, as mentioned in the earliest. We export nearly 3,000 metric tons per year. That contributes to nearly 5 to 6 million US dollars for the economy. So that is a considerably big amount to our economy, and we mainly support to the value addition. Value addition means the just after mining, whatever the activities that which increase the economic value of the graphite. So we are supporting any of those areas, as our Eddie mentioned. So research, technology development, and even startup based on novel technologies. So we have those grantee schemes, so we can support any of the university academics, research institute researchers, private and public sectors, both. So we have different grantee schemes to support all, not only the government researchers, but also for the private sector one also. I think I no need to explain this one. And if you see the key areas, because actually we have seen our records, past records, and also some data from the internet. So we have seen that mainly 5 areas. One is purification and processing technologies. So there are a lot of research on this area. And then battery anode material. So that is also one promising area. We are doing research. I think in the morning also we have seen some presentation on this one. And then graphene synthesis, converting natural vein graphite to graphene oxide and graphene. So that is also one main area. And then value addition. Value addition means product development, like reinforced composite, lubricants, rubber products, likewise. So that is also one research area. Some of the universities, they are doing research on that one. And environmental application. So there is also one area. So other than these 5 areas, some other areas also available, just like solar cells, as our Eddie mentioned. There may be some new areas also to go for research. If you consider Sri Lanka Research Institute and universities, we have 4 main research institutes, leading research institutes. They are working on graphite research. One is Sri Lanka Institute of Nanotechnology, SLINTech. So that is main institute. They are working with the especially graphene production. They have a different establishment for this one also, and also they are working on the energy storage, sensor development, anti-corrosive painting development, some of the research areas as per our records. And then Sri Lanka Institute of Nanotechnology is a partially government-owned institute. It's established by government of Sri Lanka plus 5 public sector organizations. Industrial Technology Institute is a government institute under the Ministry of Science and Technology. So they are also conducting research on graphite purification. Mainly they have some collaboration with even some private sector organizations. And also they are mainly purification, and also they are also may work on graphene production and also graphene oxide production, and some graphite used in some other areas like rubber and some other materials. And National Institute of Fundamental Studies, that is also under Ministry of Science and Technology, located in Kandy. So they are also doing extensively doing on research on this area. So they have a nanotechnology and advanced material research program. Under that program, they have some collaboration with universities also, developing local graphite for rechargeable lithium-ion battery applications. That is a main area. Even they are doing some research on solar cells and also nanomaterials and composite from vein graphite. And also activated carbon production from waste material for supercapacitors, that is graphene and activated carbon mixed supercapacitors development, and also some nanomaterial for counter electrolytic dye-sensitized solar cells. So they have a lot of researchers in there, and they are doing some extensive research on this area. And NSF has given some lot of grants to this area. Ceylon Graphene Technologies Private Limited, our CEO is here. They are also doing, especially I think they are famous for the graphene research and graphene related product research. So there is actually there is they are working with the Slintech mostly. This is a private sector organization in the country, but they have done some remarkable jobs in the country under graphite research and production. When we consider the leading universities, of course, University of Peradeniya is there. University of Sri Jayawardhanapura, that is located in Colombo, they are also involved in developing high thermal conductor rubber products by incorporating vein graphites, developing industrial viable polymer films, based sensor for foodborne bacteria detection. So likewise, some researches are going on. They will funded by National Science Foundation, some are funded by World Bank Head Project. And University of Morosua, they are also doing some research on graphene synthesis, battery grade graphite for lithium and anodes, development of photothermal membrane for efficient membrane acid salt crystallization for seawater. So this type of research they are doing. And then University of Peradeniya, of course, actually in the morning we have seen Professor Balasthi, they have mentioned some kind of what kind of research they are doing up to now. Apart from that, there are some research still going on, even NSF also funded for that one. Professor Sanjay Maliwarati, Sri Lanka graphite electrode material based on graphene composite for lithium ion batteries and solar cells, green low carbon development and processing. So going to that one, that is there. And then Uvavellasa University, they are also doing some research, especially they have some collaboration with the NIFS, National Institute of Fundamental Studies, fabricating dye-synthesized solar cells using expanded graphite. And University of Jaffna, they are also working with the NIFS, developing photovoltaic material open context of graphite-based solar application, and also novel material for secondary sodium ion batteries, membrane fuel cells. So that kind of research they are doing with the NIFS. There is a collaboration. They are research institute universities. And so the Southeastern University of Sri Lanka, they are also conducting some studies on thermal modification of vein graphite for anode material. And of course, University of Colombo, they also conduct studies on use of vein graphite to produce graphene. So that is one main product we target. We believe that we can have a more income from the graphene production. And Sajan Kotalawala Defense University, they also engage in research on titanate graphene-based electrochemical performance enhanced anode material for sodium ion batteries. So other than these universities and research institute, there may be some other research going on in the country. So these are some records with us. And National Science Foundation, we always try to give grants to our universities, our research institute, but we expect more collaboration and more partnerships. So as our AD mentioned, we have a international collaborative research program. So that is for the not only collaborate with local universities, local research institute or local industries, but also to have some collaboration with the other part of the world, maybe USA, maybe China, maybe some other developed countries, so that we expect some technologies will come to our country. So it will boost our industries and it will support to development our economy. So that partnerships are there. So we have some noticed some partnership during our research program. So one of the good partnership is the Slintech and LOEC group. So they have established that what we call Ceylon Graphene Technologies Private Limited. So there is a good partnership, and they are working on graphene and graphene related technologies. So there is one good partnership. We believe that it will boost our, they will support to boost our economy through this production process. And also we have seen there are some partnership with the University of Sri Jayawardhanapura with Bogala Graphite Lanka PLC. I think some gentlemen are here from Bocal Graphite Lanka PLC, and also Slintech, CGTL, and then University of Peradeniya and Bocal Graphite. They also have some partnership for commercialization graphene-based product, and then ITI, Industrial Technology Institute, and Bocal Graphite. They have some partnerships, and then ITI and Ragajara Graphite PLC. They also have some partnerships on commercialization of graphene-related rubber technologies, and then University of Peradeniya, University of Colombo, and Sarasavi Industries. They also have some partnership. So we have we have noticed this kind of partnership, and that is a progressive part, because as our AD mentioned, that even if you do research in our silos, because research will end up with the publication, maybe research will end up with development of technologies, but if you do not translate that research from lab to market, that means beyond the lab, and it will bring to the industry level, then only we can use that research result to development our economy. So that's what we always target. That's why we are also promoting collaborations and partnerships. Even if one university can join with some other university research institute, and also with industry, they can do some research, and it will, we believe that it will support to economic development. So if you see the recent development in our research in graphite technology, so we see there are a lot of application from mineral processing technologies, and also for the graphite also, there is a good indication that our researchers are working on this sector, because even our government also believe that because minerals, graphite means our natural resources, that is, we have that raw material. So if you do research on that one, and if you have a new development, new technologies, and if you can increase the economic value of our minerals, graphite, and if you can export that one, so then we can have more and more forex from that one, for income from that one. So that's what we always thinking, and we are supporting that one. So National Science Foundation, as a funding organization in the country, we always like to support our researchers for their research on graphite, and also if they have some collaboration on this theme with our US researchers, experts, or their industries. So we are always happy to support that one, and we expect that type of partnerships and collaboration in future. So that's what we expected from as a National Science Foundation. So with that, I end up my presentation. Thank you.
Thank you very much. And we now move to our second theme, industry needs and market perspectives related to graphite. This will be conducted as a moderated panel discussion featuring distinguished experts from both Sri Lanka and United States. It's my pleasure to introduce the moderator of this session, Ms. Tilina Kumari Kandanamulla, Senior Scientific Officer at the National Science Foundation, Sri Lanka. She will take over the session from now onwards.
Thank you, Dr. Nadisha. Now, as she very correctly mentioned earlier, today the National Science Foundation will be doing this practitioners forum as an overview to certain prominent themes that we are discussing today and tomorrow. Perhaps this session that we are going to do now, start now, would provide an overview to tomorrow's extensive discussions on industry perspectives and potential collaborations. So, first of all, let me invite the team of panelists, both from Sri Lanka and the US. Let me invite Engineer PVI Hemalal, Chairman of the Kahatagraha Graphite Lanka Limited, Sri Lanka. So please come to the podium and take a seat. I think he's in the audience. Yeah, I would like to invite Engineer Mr. PVI Hemalal, Chairman of the Kahatagraha Graphite Lanka Limited. And as the second panelist from Sri Lanka, I would like to invite Mr. Manju Gunawadana, Chief Executive Officer of Ceylon Graphene Technologies Limited, Sri Lanka. Please come take a seat at the podium, at the head table, please. Sorry. Then there are a couple of panelists from US as well. Dr. Igor Basukov, please excuse me for my pronunciation if there's anything wrong. Technology and Business Development Manager, American Energy Technologies Company, USA. Please. And I would also like to invite Dr. Anthony Burrell, Chief Technologist for Energy Storage, National Laboratory of the Rockies, USA. Please take your seat. Right. So there's a coincidence, very significant one though. Yeah. Right. So let us start the panel discussion now. So as an introduction to the panel, I would like to give a few points, few thoughts, this forum, this segment of the Practitioners Forum on industry needs and market perspectives in graphite is at a crucial intersection of geology, technology, and market transformation. And throughout today, we discussed about graphite petrogenesis to battery-grade applications and global supply chains. And this will add some perspectives and some more value to that discussion that we began. And also, today, graphite is a strategic material central to energy storage, electric mobility, and broader critical minerals landscape. So there's a growing global demand for high purity graphite in advanced technologies. Now I would like to invite our distinguished panelists to introduce themselves. So please take 1 to 2 minutes and introduce yourself to the audience. Let's begin from Dr. Burrell.
Good afternoon. First, I would like to thank everybody for this wonderful meeting and being invited. It's not coming through very well on the microphone. I will try harder.
Okay, great.
Thank you. I can certainly talk louder. So I want to thank everybody for inviting us to this really prestigious and important meeting. And I and certainly for holding it in a wonderful country and a wonderful location. So I know we keep getting thanked for coming. I actually want to do the opposite. Thank you for letting us come. This has been really, really positive for us, and I want to be clear on that. So who am I? I'm Tony Burrell. My name's Anthony, but Tony Burrell, and I work at the National Laboratory of the Rockies. For the last 15 years or so, we've been focusing on expanding and directing the energy storage and lithium-ion systems and across the board. In the past 5 or 6 years, it's become very apparent to us these technologies have advanced to the point of commercialization and accelerating, but where you get the materials to make them is a critical issue that we have to address. So at the National Lab of the Rockies, we're really interested in not just how do we advance the technologies, but how do we advance the production of the materials and the minerals that get them into place. So all of these aspects of where we mine, how we mine, and how we process. The specifics of graphite are a little complicated because not only can you dig it out of the ground in different qualities, and we've seen a lot of that today, you can make it synthetically. This really comes down to a couple of things that we need to think about and that we think about is cost and cost and cost. We need to be thinking about how we use these resources and where we go, and that's really where our scope at the NLR is how do we get these materials, how do we accelerate them into the supply chain, and that's something that we've been working on a lot as we go forward. So I'm really looking forward to the discussion about how we do this and where we're going.
Thank you very much. Let's move on to the next panelist, please.
Yes, Mr. Selena Kumari, it's a pleasure. Thank you for bringing me on this panel, and what a pleasure to speak in front of such an esteemed audience. So I'm Dr. Igor Barsukov, okay? I've been doing graphite since 1987, and my PhD was on Sri Lankan graphite, brought to Germany by GK, Graphite Crop Miracle, right? So the very first intercalation battery, at the time lithium-ion just appeared, so it was an aqueous system. So I've been living graphite world and enjoying it for my entire life, right? So if you look at the market, in the market you have people who mine graphite, or who make precursors for synthetic graphite, calcined petroleum coke, for example, and you have processors, right? So we are a proud downstream processor, okay? So for us, high tech has always been the key. We've been manufacturing graphite for batteries since 2010. We got our first product approved in 2010. And right now, majority of battery companies, which are not your mainstream EV producers, but rather specialty battery producers, they tend to use our materials, okay? And besides batteries, we identify approximately 600 other markets for graphite. Usually you look at graphite as a pie chart consisting of friction, metallurgical, batteries and such, maybe 5 segments, right? We identify 600. So it's the art is to understand those segments and to operate in them, okay? So we can take your graphite, wherever it's mined, in whatever condition it comes in, and we can upgrade it using our furnace technologies, which are located in Chicago, to 99.9999 plus, so nuclear grade purity graphite, or for battery 99.95. And then we have every technology which is out there for spheroidization, for carbon coating, shaping, grinding, sizing, whatever is needed, right? So that's our little world. We come here with industry perspective, and we are very open in looking at opportunities for Sri Lanka. Thank you very much.
Thank you very much. Next, from Sri Lanka.
Welcome to everyone. I'm Manju Gunawardena, the founder of Sri Lanka. I'm one of the members of Sri Lanka Institute of Nanotechnology and a founder of Ceylon Graphene Technologies. We started Ceylon Graphene Technologies immediately after the Nobel Prize in 2010 with colleagues from Sri Lanka Institute of Nanotechnology as well as Colombo University of Colombo. So we wanted to find a new technique to convert Sri Lankan vein graphite into value-added materials for real industrial use. So we started our research work in 2014-15. Then today we have 3 industrial operations happening a couple of places in the world. One is in Sri Lanka. We are the largest graphene oxide manufacturer in the world currently. I don't know about China, but the rest of the world. Then we have 2 other manufacturing plants. One is in India, in Bhopal. The third plant is in Abu Dhabi, in Khalifa University. Our idea is basically to add value into Sri Lankan vein graphite. Currently, we export Sri Lankan vein graphite to various places without any significant value additions. Our idea is basically to add as much as possible value into our material. Is the first exercise. The second exercise is basically to give plants or fabricate plants to various industries for them to produce their own graphene oxide for their applications in situ. Because when it comes to the characteristics of graphene oxide, we have realized that which is a very active material and very, very prone material for slight changes with different parameters like temperature, UV exposure, and various physical parameters can immediately change graphene oxide into different forms. So what we push currently is to produce their own material at site in different industries around the globe. So we are putting up facilities around the globe now. So the second and the largest in the world is going to be in India in another 2-3 months' time. In another week's time, we are going to start our first Indian facility up and running. It's already commissioned. So Sri Lankan vein graphite will go into various places, convert them into usable, applicable, different materials according to the industry, and country will be getting the benefit. That is that was the main idea for us to start Ceylon Graphene Technologies. So thank you very much, National Science Foundation and the Fulbright Commission for this opportunity, and it's very, very happy to see this level of knowledge in graphite here in Sri Lanka. So this is going to be a fantastic start for the future. Thank you.
Thank you. Last but not least, Engineer P.V.I. Hemalai. So please introduce yourself.
Thank you very much for giving this opportunity to speak to you as a panelist here. I am a professional mining engineer, a chartered mining engineer. I started my career about 45 years back as a junior engineer at Bogala Graphite, and I spent nearly 10 years in graphite mining and as a purely engaged in engineering and then in management. And we did a lot of work, how rock mechanics is applied, how to improve the ventilation systems there, how to improve the mine infrastructure, shaft sinking, and a lot of areas with great interest I was engaged in, purely on engineering. Then I served a period of 13 years as the general manager and chief mining engineer of the only phosphate deposit in Sri Lanka. And after that I was asked to join the university, the Department of Mining and Minerals Engineering, University of Moratuwa. Actually, I regret that it was no mention of that university was not made today. The type of research they are doing, University of Moratuwa. It's a mining engineering faculty, the mining engineering department. They are also doing a lot of research, but not basically on graphite research, but a lot of mining research they are doing. And I did some consultancies after leaving the university. The most recent experience involved working a period of very absorbing and enlightening and unforgettable few months at Oman, covering the entire Al-Hajjar mountain range from Indian Ocean to United Arab Emirates, covering 11 sites as the project manager of a team exploring for building materials and making basic mining plans for them for the Omanese mining ministry. So after that I was a consultant, and doing my consultancies, sitting peacefully at home. Then the Honorable Minister of Industry and Entrepreneurship asked me to take over the chairmanship of this mine, Kahataka Graphite. Even now I am engaged in very much, even as a chairman I have to undertake certain areas of development, the Kahataka mine, which you will be visiting a few days later, day after tomorrow on the 30th, is the deepest and the largest mine in Sri Lanka, but not the best managed, I would say. I took over 1 year back, surely, and my task is to develop it. And it has a very large infrastructure, which you will see for yourself. 15 kilometers in length. Underground tunnels, drives, you call them winzes, so galleries, everything together. And I have to seriously concentrate myself, concentrate on mine ventilation, because I have been the principal mining lecturer at the University of Moratuwa during my entire period. And we face in Sri Lanka, at the deepest mine in Sri Lanka, the challenges of rock temperature, almost equal to the body temperature of 36.9. Those are some challenges we are tackling. As the chairman, I have to do it, because there's nobody else, I would say, with experience in that. And deep mining, rock pressure manifestation compared with Bogala, and very many areas I'm tackling, very many technical areas. So I'm engaged in these areas, and the biggest challenge is developing the mine to bring up to modern levels. That is my challenge, and I think I have undertaken that challenge and going ahead.
Okay, thank you very much for that valuable introductions. Now let's move into the round of questions. Each panelist will get around 2 questions. I would like to kindly ask you to limit the duration of your reply to around 2 to 3 minutes so that we could save some time for the audience to ask some questions. So let's begin the round again from the Sri Lankan panelists. That is, let's move to again to Engineer P.V.I. Hemalal, Chairman of the Sri Lanka, that's Kahatagaha Graphite Limited. So, Sri Lanka has a long history of green graphite mining. From your perspective, how traditional mining operations evolve to meet the quality and consistency requirements of modern battery industries?
Sorry. A traditional mining operation. First thing I see, traditional mining operations, you all heard about that there were 3,000 mines operating. All were traditional mining operations. The Sri Lankan perspective, what's a traditional mining operation? No exploration, without any exploration, the landowner detected a vein. Very often the Sri Lankan veins are steep dipping, and went down the vein, sank a shaft to a depth of 30 feet, 100 feet, and the shaft was closed. The main challenges were, limiting factors were the water and hoisting by hand, and adjacent pit was sunk. They were not worried about what came out, just raw graphite was sold out, sold by a trader and exported. So this is traditional pit operation. It was a pit, it was not a mine. And out of the 3,000, just give me 1 or 2 minutes more, 2 mines stand out. Bogala, Kahatagaha, and Ragidro is also a small mine. What stands out is the owners were big landowners who had enough capital and they had the money to invest. Bogala, owner from 1930s to 1940s, he had developed a lot of contacts with England, where mining was very much developed in Cornwall, Camborne. While studying there as a student, the future owner brought British mining engineers who had experience in vein mining, gold and I think tin, yes, tin mining. 3, the names I can still remember. From all records. Christopher Renault, Derek Morris, Brian Hopwood. They ruled the mines for 30 years and made a beautiful infrastructure. The infrastructure was consistent with the development of the mine, ventilation, and all aspects of mining, a good residential village for mining families, like the Peradeniya University. So that's how Vogel stands out. And they are doing their upgrading to a certain extent. I am not authorized. I think Mr. Jaisingh, my good friend, is here to talk more about that, because actually they are well ahead. How they went ahead, they got the expertise engineers, they got the capital, and the owner has some foresight. 3 things necessary. At Kahatagaha, the former owner was a former prime minister, very rich man. He developed a good shaft system, installed the best winder still in Sri Lanka, but in different areas they failed. One common feature which was lacking was exploration. If we are to ensure the quality and consistency needed for graphite, for battery industries, we should look at the point of view, and we should consider the whole value chain, starting from exploration, mining, processing and value addition, and marketing. Exploration has been an area which has been thoroughly neglected. Everybody did mining, but not much of value addition or processing. So that's an area, the requirement of the time to develop that area, to develop into not only quality-wise, but also the throughput, consistency, the production levels necessary to ensure a consistent market.
Right.
This is the difference between a traditional pit and a modern mine. I am now very happy to comment for the first time in Sri Lanka, I think Magosa. I am familiar with the mine, and they did, firstly I think they did some 10 years back, heliborne survey of the area. They went down and did diamond drilling. They established reserves. As I can remember, it was 2.2 million, 2.5 million, because I was also to a certain extent connected to them, and I am very happy to hear that they are starting mining.
Right.
They are starting mining. That's the first ever mine starting very methodically. I think they will have a very good future.
Thank you. So thank you for that detailed answer. And let's now move to Dr. Igor Baskov. I would like to ask you, how do you evaluate the commercial readiness of natural graphite sources, such as Sri Lankan vein graphite, for integration into global battery supply chains? Some things in relation to the previous question as well.
Yeah, specific to batteries, right?
Yes.
All right, so colleagues, we should differentiate between different types of batteries. There are approximately 30 commercially viable battery systems, and we are all familiar with, dry cells, which are carbon manganese dioxide batteries, of which people make close to 12 billion per year. Okay, then these are called dry cells, right? You also have alkaline cells, almost in every country they're being produced. And those are made in quantities of about 10 billion cells per year. You also have lithium ion with a huge push and overcapacity. Last year, there were 12 billion cells produced, predominantly in China and in South Korea, right? And we have to also recognize that there are lead-acid batteries in traditional cars, right? So the art would be to understand where specifically Sri Lankan graphite, vein graphite would fit. So I can tell you that, I've been here in Sri Lanka for 15 hours now, and I've heard there are some voices which are rather pessimistic about a prospect of Sri Lankan graphite in lithium-ion market, which I don't agree with, actually. There are sub-segments within lithium-ion market, and I wouldn't advise going after electric vehicles, because if you look at the numbers with the total capacity of Sri Lanka vein graphite, let's call it 5,000 tons per year, just for sake of calling it, right? The reality is the number is much lower. And with the demand being 200,000, right, in natural graphite that went into lithium-ion batteries last year, that's going to be a drop in the bucket. Plus, prices which lithium-ion batteries are willing to pay are dictated by China, and unfortunately they are extremely low, right? So let's not go after electric vehicles, but let's go after batteries for BESS systems, battery energy storage, which are green utilities, solar and wind power generators, which have container loads of batteries next to them. And those predominantly use natural graphite. There are huge opportunities for natural graphite there. And let's not forget about specialties. Of course, we come from a country which requires a lot of military batteries for whatever reason. So natural graphite is used very heavily in those systems, okay? Now we have to differentiate between spherical graphite and non-spherical graphite. And I invite people to attend my presentation tomorrow, where in one process, in one go, we're generating both spherical and non-spherical. So those non-spherical materials, they're called also spheridization rejects, and they are just ideal for lead-acid batteries or for alkaline batteries in almost as is state, right? So what would it mean for Sri Lanka? For example, there is a world-class company called Energizer, which operates a BPL India plant in India, right? So which is literally next door. So why not supply graphite to Energizer plant in India, to BPL India? That's a very concrete example, into alkaline batteries, and people there are just dying from the increased tool wear in pressing battery cathodes, which are manganese dioxide based. As you know, manganese dioxide is highly abrasive. And this is where they need not just electrical conductor, but also a lubricant, okay? So there are multiple segments. The importance is to understand your market, to really understand which segments you go after. And yes, there is absolutely room for vein graphite from Sri Lanka in lithium-ion batteries. It's just not necessarily in electric vehicles, okay? But you wouldn't be able to produce enough graphite for electric vehicles anyway. So your option is to go specialties, and those specialties can pay much higher price, and that's the situation on the ground, right? That vein graphite unfortunately costs more or sells for more than flake graphite, but the benefits which are coming from vein graphite significantly outweigh that price differential, okay? And we can talk more specifically. I can give you more examples. Anyone who is interested in those directions, we can talk.
Right.
Okay.
Thank you. Thank you for that answer. Now, I'd like to ask the next question from Mr. Manju Gunadana. So, as a leader in graphene technologies, how do you see the transition from raw graphite to high-value graphene products shaping Sri Lanka's industrial future?
In the first place, I want to thank him for a super eye-opener to everyone in this country, because each and every person who got something to do with graphite in Sri Lanka is under the impression that we can simply supply it into the battery anodes, or lithium-ion batteries, which is, he explained it very beautifully. Our capacities and the amount of mined capacities currently is not even come close to the global requirement of graphite for lithium-ion battery large-scale anodes. So here, as he correctly said, I'll start from there. How to convert our material into specialty products is the key here. I really would like to mention one of our the prominent research scientist in my graphene journey is here. Dr. Dilushan is just here in the audience. I just saw him. So idea was basically to convert and to tap the special features of Sri Lankan vein graphite to the graphene world. So graphene can be made out of even flake graphite or any type of graphite, but how to tap the maximum potential of Sri Lankan vein graphite, the crystalline properties and the aspect ratios and the sheet size capabilities of Sri Lankan vein graphite in the graphene game was the main idea we had in our mind. So when it comes to conductivity based applications, whether it is electrical conductivity or thermal conductivity, we have a very prominent edge by using Sri Lankan vein graphite into graphene oxides, then subsequently into reduced graphene oxides. That is our area. And very good example, he just started talking about batteries. Yes, we developed the first lead-acid battery using graphene oxide as a dopant, not as an additive or a main material, by applying 0.32% of graphite or the graphene oxide, reduced graphene oxide basically, into the negative active material of a lead acid battery, we started getting 30-40% improvements in dynamic charge acceptance, and cycle life improvements by 200 to 220% due to less sulfation on the plate. So those are the key areas we should think of. Not to go and fight with large-scale synthetic graphite manufacturers or with general graphite manufacturers was top in the list here. So this is one area. The second area is building material manufacturing with graphene oxide. We are in the forefront of producing building material, cementitious material additives in the world. We are working with large companies like Sika and BASF. We have developed GO-based additives, superplasticized additives, to improve the tensile strength as well as the compressive strength in cement and concrete-based applications, which is going to be something very big. We've been working in this particular subject from last 8.5 years. Now we are 100% successful. We now push products to the market. Our partners are Sika, BASF, and Sigma Chemicals from India. So likewise, the major focus has to be adding value into the specialty graphite we have to solve specialty and niche problems, not to go into large-scale production. Then it's going to be, we produce only 3,000 to 3,200 tons a year, which is a negligible amount when it comes to the graphite sphere in the world. So when it comes to graphene, 1 kilogram of graphite can produce 1.4 to 1.45 kilograms of graphene oxide. So 3 kilograms of graphene oxide can produce 1 kilogram of reduced graphene oxide, which is a super area for us to tap. We have secured a couple of patents here in Sri Lanka. We became the largest graphene oxide manufacturer, certified graphene oxide manufacturer by the World Graphene Council. So we have a couple of facilities up and running. A couple of members here witnessed our facilities day before yesterday. And we are putting up some more facilities around the globe to supply material into that particular industry, not to the major graphite industries. Thank you.
Thank you for that informative answer. If we move on to Dr. Burrell, what are the key performance and sustainability considerations when selecting graphite materials for large-scale energy applications? What are your thoughts?
So I want to begin by being clear about applications, stationary storage applications. But these are not areas where a high-cost graphite can play. It's actually the difficulty in that area is the margins on those products are much less than they are on vehicles. So you're right about one thing, though. It's only about 10% of the total global market for EVs in that space is total, megawatt hour capabilities. So I think there is a clear option for Sri Lankan graphite that people haven't really thought about here, and that is it's already being mined. We saw a number of reports from the US where we're looking at resources, we're looking to develop resources. This is something that is at production or being scaled to production. So it is available to the market today. So that makes it very valuable in specific application space. The challenge I mentioned before about cost and the availability of potentially synthetic graphite, wow, it's getting getting weird echoes, is that you're really dealing with a supply chain problem. So right now, almost every piece of battery-grade graphite flows through China. The specs on those are very good. So if you're going to be producing graphite for a market, whatever that market is, you're going to be competing against a low-cost product with high specs. Purity for battery applications, first cycle efficiencies, longevity, all of these pieces play a really important part. This can be done, it's just at what cost? I think Igor mentioned one of the things that really, there are specific application spaces where supply chain control and verification are very important. So if you're thinking about, and I'm going to use defense application spaces or critical infrastructure application spaces, not just in the US, but across the entire world, and you have security concerns about supply, is the supply fake? Is the supply being diverted from places where there's embargoes? The ability to basically map that supply chain, produce product at purity, shouldn't be underestimated. So I don't think the scale is everything. I think you're right. There's no way that Sri Lanka could supply the global market for EVs. However, people do offtake agreements that capture the entire market for certain mines. So this is something China's done a lot. There is opportunity, I think, if you can get the right connections and purification processes and keeping the cost down. No one is really willing to pay for a significantly higher product, even in some of those spaces. They might be willing to pay a margin higher, but you can't do 5 times the cost or twice the cost and hope to grow that market. But I think if you're in a situation where you have a guaranteed supply, which that can be controlled and mapped, there is some applications and spaces where people really do want to know the material they're getting is reliable from a clean source, from a non-labor forced organization and other applications like that. But the key thing is you have to meet specs. So that means battery not close to, you have to be at the commercial specs for the materials, say, coming out of China or South Korea or Japan. That's going to cost money, and the question is, can you do it at scale? But I do want to remind you, you're already producing graphite where many people are looking to find the resource.
Sorry, we're having trouble with the online, so if you could move the mic a little closer.
Okay.
It's too quiet. Thank you.
Seemed very loud in the room. Okay. So, I mean, that's my point, is that we're looking across the world to develop graphite resources. Australia's looking at its resources and how it can develop. You're already producing. I think you should grab that opportunity and run with it.
Thank you. Thank you very much. And I think we could go for a quick second round of questions before we engage with the audience. So I would like to ask the next question from engineer Mr. Hemalal. What is your perspective regarding the term value addition? Can you elaborate on the value addition and what is the general direction that you recommend?
It was much discussed here,
Okay.
real people who are really engaged in.
Right.
So as I concentrate more on our mine, my mine, Kahataka mine, and value addition is an area which has been, to tell you the truth, has been neglected in the history. So type of value addition which has been done is very primary level. Not even flotation we have resorted to. What definitely we should go for is secondary and tertiary levels to go into higher levels of value addition. That is our main intention currently, to get the maximum value of the crystalline, high-grade graphite product. Actually, the product which is coming out of the mine is 100% 90 plus. And currently what we are doing is insignificant, rather I would say. We upgrade the graphite content to 99.99 plus. These are basic operations. And particle size reduction. And these are some basic grades we are sending to the market. But I will combine my next questions as well. Currently, the mine is going to be developed into a major operation, which is coming under the Ministry of Industry and Entrepreneurship Development. The ministry has launched a drive to attract prospective investors to develop this mine. This 150-year-old mine, we have a huge infrastructure which has to be widened, which has to be explored, which has to be, the mineral reserve has to be created, to sustain the future operation. It has been in existence for the last 150 years, and it has to go on because we have the greatest strength. We are in the graphite country. The Kahataga Ragedara graphite corridor, I think it has more than 100 odd mines, and those are to be developed. We have to go out of this mine with collaborative efforts and develop the throughput necessary to go into higher production. Firstly, establishing the reserve. So right now, the EOI is underway, and world, a lot of investors have expressed their interest to invest in this, to explore the mine, to mine it, and above all, to produce graphite-based end product development for the future. So this is the current program which is underway. And I believe that it will work out. So this is our future direction, of course, value addition.
Right. Thank you. And the next question to Dr. Igor Vasukov. Now, what can international partnerships play in bridging the gap between the resource-rich countries and the technology-driven markets?
Well, it's all about being in global markets these days, right? So you cannot imagine a country just boiling inside itself and coming up with something. So resource quality is question number one, right? Where do you get your raw material from? In this case, it's graphite. If you know that your graphite is coming as non-blended product, right? If it comes from the same hole in the ground, that's already very reassuring. Large institutional buyers, like our customers, they want you to go down to the source, and they are trying to understand what your source is, right? And we obviously are not telling, but it's very important to have assurance that your graphite comes from the same source. So from this perspective, here you have one aspect of it, right? So, but I think we're seeing more and more that from just being the supplier of raw material, countries, and not necessarily just Sri Lanka, right? You see it a lot in countries of Africa. Local governments are starting to demand that more value-added processing be done in those countries, right? So that more value is actually absorbed by local countries, right? And I think that is a very important aspect, right? So you could be supplying a semi-processed product. In case of graphite, it could be like graphite for lithium-ion batteries. It could be spherical unpurified graphite or classified graphite. So the only question is, where do you get the money, right? So to build a downstream plant, that's $100 million. Who's going to come up with $100 million? That's even existing applications, even existing mines don't have the revenue to even justify that. So you need some high caliber investors, so you need a national level program which will come up with $100 million or $200 million to install a model plant that would be doing it. And expertise from the West is available. That's for sure, and that would be an example of international collaboration, okay? But unless and until there is a very visible mechanism of how do you actually find $100 million and bring it to Sri Lanka to build a downstream processing plant, it will more or less continue to be, resource-driven and looking for partners who are operating out in the West. All right.
Thank you. And from Mr. Manju Gunardhanan, I would like to ask, actually this was mentioned at one point during the presentation by Dr. Nanda Balasuriya today morning regarding the industry-academia collaborations. According to your view, how important is industry-academia collaborations in accelerating innovation in graphite-based advanced materials? Do you have any examples and thoughts on that?
I have millions of examples for that, because I think we have performed our 3,000 sample from my factory to different academic institutes throughout the world. We used to send samples. I have a policy. In my organization, we have a policy, and we offer graphene oxide or any specialty materials from my factory 100% free of charge for academia. So this is one of the decisions I have taken to strengthen the question or the situation we are in. Now, the best example is not here in Sri Lanka. The best example is actually from Khalifa University from Abu Dhabi. They wanted me to come and install a plant in the university. The idea was to produce graphene oxide, to give those materials or the specific materials or mission-specific graphene oxides developed within the university, to give it to the application developers in different departments in the uni to come up with their prototypes. The biggest problem is, as an academic member or a researcher, you can buy graphene oxide or any other carbonaceous material from various other vendors in the web, or from Sigma, or from various places. But once you are successful with your research and once you have a proper prototype in your hand, before you go and talk to the industry, you should have a supplier for this material, because every graphene oxide or every graphene is not the same graphene. You need specific material for your application, right? Fine-tuned specific material for your application. So those are the mission-specific materials. So you can't simply go and buy it from the corner shop. So you need a proper supplier for you to get into industrial scale. So we are a Manchester Geek member as well. So Manchester Geek as an organization, as an academy, the private sector academic incubator institute, they are facing the same problem. They develop nice products, but they don't know how to go to the scaling up process, because they don't have a proper supplier. So Khalifa wanted to resolve this problem by having a graphene oxide manufacturing facility within the organization. The organization is called RIC2D, which is an incubation and a 2D material research center within Khalifa. And we installed a unit where we can produce 1.5 to 2 tons of graphene oxide per year. It's a small plant, fully automated plant. You can produce mission-specific or different types of differently functionalized materials in that plant. So we give materials to the students. They develop products. Once they are ready to go to the market, we have our large-scale facilities in Sri Lanka and in India to produce the same material in larger scale. Otherwise, there's no go, because they can buy or they can get my material, develop everything. Once it is perfectly working, when you go and buy it from China or somewhere else, it's not going to work. And we have ample experience, and we have very good the case studies in that. The biggest problem is we have no international standards for this particular material, because since the material is new, we don't have ISO standard, we don't have any ASTM standards for graphene oxide. Luckily, after 11 years of a huge battle, we ended up with having a small or preliminary type of a ISO standard for graphene nanoplatelets, but not for graphene oxide or for pristine graphene. So now we are trying to get into that with ISO to have international standard for graphene oxide. Otherwise, when you really want to buy some material, you go and order material from another vendor, especially from China, and you get something black, which is not graphene oxide, or which is not the material that you exactly want. And characterization is not easy. You need a proper laboratory for characterization. You can't simply have all the equipment inside your lab. If you imagine you are a battery manufacturer, you don't have SEM, STEMs, you don't have XRDs or anything in your lab. So you have a dependency in that case. So it's not an easy scenario to maintain the quality as well as the repeatability of your results if you don't have those infrastructure. So to resolve that, we started giving samples, having our large-scale facilities. So if someone wants to use our material, come up with solutions, come up with your, let's say, TRL level 3-4 prototypes, and we are ready to supply large-scale materials for them to go to the industry. So like that, we have bridged that gap.
Right. That's a good message for our young innovators as well. And as the last question of this panel, I would like to ask from Dr. Burrell. So how do issues such as supply chain security and critical mineral policy influence research and industrial priorities in the United States? Now this question has some connectivity with the next segment of this forum that we are doing on policy. Please.
So I think the first thing that pretty much everybody realizes is, and I think this became abundantly apparent during COVID, that single point failure supply chains are just not sustainable in this world. Despite, that's aside from political differences that impact trade. So pretty much I think everyone, and it's not just the United States, Europe, Asia, the rest of the world are looking at how do we diversify supply chains for these critical mineral pieces. Diversifying supply chains does not really mean taking a single supply chain and splitting it into two sources that get shipped back to another country. That's not a practical outcome. That's a good way to disguise your supply chain, but it doesn't solve the problem. So when we think about supply chain security, it is understanding where it comes from, how it's supplied, and there is more than one potential supplier for any key component in a system. If you have, and I remember when the port of Shanghai went down, not because of anything political, not because of anything, because COVID shut it down, the battery industry in the US almost ground to a halt. They were flying their products across the ocean because they needed to keep going and they could not find another alternative. So I think one of the things that all of us are looking for is diversity in supply chain. And secure supply chains are not single point failure systems. They are diverse supply chains where if I'm purchasing from you and for some reason you have a typhoon come through and shuts down your factory, I can move to someone else and supply that product. It may not be the same cost, there may be other issues, but there are more pieces to that. So I think that's one that we tend to forget. It isn't about can I own my supply chain, but can I have a secure supply chain as we go? The other aspect of that is ensuring that we have a developing supply chain across the world. So when we talk about how industry, and this sort of came up with the how do government and industry work together, how do we do this internationally, there is natural synergies across different systems as we go. We all do not have to develop the entire supply chain by ourselves if we can work together to make sure that those synergies are working. So when we're talking about $100 million for graphite purification, I think that's one where government to government interactions to spur those conversations about how do we get $100 million, it's a good number, for a graphite purification processing plant in Sri Lanka. And how does that help Europe or the United States or other countries synergize their work, not own everything, but diversify and ensure that supply chain. So I think part of it is government to government discussions that incentivize industry to put this investment in. One of the concerns about industry is if I do this investment, is it going to pay off? How long is it going to pay off? Obviously, things like tax incentives or loan guarantees or things like this do play. And I think we've seen more recently, certainly in Europe and the United States, more opportunities where the government is willing to back mining interests or processing interests for critical minerals. My personal belief, that doesn't always have to be inside the United States, as long as it shores up and diversifies our supply chains. So I think there is more mechanism for this, and unfortunately it requires politicians to be involved, which is always a complicated piece. But that's where I'm at.
Right.
Thanks.
Thank you. Thank you for your views and insights. Now we have 5 minutes remaining. So I would like to invite the audience, if you have any views, suggestions, thoughts and questions for the panel or in general, please raise them. Yeah, yes, please. Please introduce yourself as well.
My name's John Shackleton. I'm the Managing Director of Margosa Graphite. I am somewhat confused. I think the panel have done a great job. I am somewhat confused by the message, because the way that I read this summit, this is a graphite summit for Sri Lankan graphite to get assistance from the US. And I listened to the panellists and I agree wholeheartedly, specifically about the battery side and the EVs and all this, and I've said that also. I dismiss graphene. I think graphene, as much as it's a future material, I believe in it. Graphene is a word that's bandied around like confetti. And I think that starting right here, right now, the assistance for Sri Lankan graphite has been mentioned numerous times, and I don't know if anybody's taken the hint, but it starts with resource. It starts with a specific resource, because without a resource, this country does not have a graphite industry. It has mineralised anomalies. So if we want to be genuine, we all need to band together and ensure that the research and the work is done correctly to prove to the world that we do have graphite here. Secondly, moving from that, Manju, I've got to ask the question. You clearly state now, and you've stated many, many times at many conferences, we don't need to produce a lot of graphite, because you can make 1.4 kilos of, well, I won't say graphene, RGO, because it's not graphene. Let's use the word graphene as it should be defined. It's an ISO-defined term. You make reduced graphene oxide like everyone else does. Great product, yeah, find a market, excellent. But you're stating that you make 1.4 kilos of that. We export here 3,000 tonnes, so you can make 4,200 tonnes of RGO. That is not going to save this industry, or that's not going to advance Sri Lankan graphite to where it needs to be. The reason I raise that is because politicians in this country listen to the academics. And if the academics are saying that this industry is going to be saved by graphene, and it was very obvious when the EOI came out for the Kaharikaha mine, where it simply stated in one of the sections is you must make graphene. The politicians don't understand the definition of graphene. So if you've pigeonholed a very good project, which I believe Kaharikaha has a future. If the politicians think that you have to make graphene to be able to operate that mine, well, I don't think the mine's going to advance. I don't think the world's going to come in here and rush it to take Kahari to the next level. So where I'm coming from is we need a combined pitch. We need the geologists of the future in this room to understand they need to work at resources. We cannot make assumptions, and we cannot advise politicians, especially in Sri Lanka, who write policy based on value add, and the value add at the moment is graphene. So no one will be able to, if we let them go on their mineral policies talking about graphene, this industry will never get off the ground. There are many, many, many applications, precursors to graphene. Let's get serious about some of those applications. And batteries, I agree, batteries aren't the answer. Yes, we can fit into batteries, but at what cost? Right. So the US have given everyone in this room an understanding right now as to stop thinking about you're going to make millions of dollars and we're going to save an industry here by getting into EV batteries, because we cannot compete against China at all.
Okay, let me answer. I think it is the question well taken. But first of all, I must tell you one simple thing. I didn't mention that I have my own mine. I don't depend on Bogle or any other mines, because my major focus is making graphene oxide and reduced graphene oxide. So I'm an outlier in this entire conference, because I have my own mine. We convert my graphite into graphene oxide, and we reduce it and we sell that. So I have no right to answer on behalf of the graphite industry. We are one of the very rare situations where we have our own mines, we have our own technologies to convert, and we have our own application development teams, and we have our own state-of-the-art laboratories in the organization to support the industry I'm in. So I think I can be away from this particular question, because it is a niche industry where I convert my graphite into whatever I really want to produce and sell. As far as I can earn money to the country, I think that is the way forward in that. But I know by doing your explorations to the point, adding value into the industry per se from last 10, 12 years, you have that problem, and you definitely should resolve this matter with the officials from the government. It is a very valid question he asked. He's from the government mine and he's stuck already with the same question, or he's not in a position to answer if you ask him the question. So graphene scenario is that, and graphene is not the ultimate material you can, or not the only material you can produce or you should produce with graphite. I'm 100% agreed. I have expertise to produce that better than most of the people on earth. So we have a market, we do it. But I think it's a high time having all these people trying to attract investors and sciences, technologies from various places in the world to this country. The country should have a proper, clear pathway and a guideline to add value to their own resources. There is a government scenario. I think it's a valid question, but you asked something about graphene, so my answer is that. Yeah, of course, that 1.4 kilograms of graphene oxide from 1 kilogram of graphite is not the equation here. I'm an outlier simply in this game.
Right. So I think in the interest of time, we have to stop here.
Take one more question right here.
Yeah, all right, sure. One last question, please.
Hi there. Alistair Smith from Acroma Group and Critical Outcomes Group. On the processing that you think would be viable here in Sri Lanka, what state do you think and what level of processing should be done so that it's most appropriate for sale in the Western market?
Well, I'll take this question, okay? So let's start. Where do we start? In my opinion, and John, I'd like to echo that. It should be a graphite story, okay? And I'd like to tell you, we use a lot of vein graphite. We use it despite its higher price than what it is in the market, because it has some absolutely unique properties, higher thermal conductivity, high electrical conductivity at high density. This is where the sweet spot for Sri Lankan graphite is, not to mention lubricity. So, if I was running the show, right, the first thing I would do is I would put in a mixing plant. I would start making graphite paints and coatings, because your customers are paying for a gallon of paint, right? Of which up to 20% is graphite. So that's a market, and that in of itself has 100 different applications. Somebody mentioned anti-corrosion. Right now there is a new market, stealth technologies, drones, what we know from Ukrainian war. It's all about ice-phobic coatings. These are high-tech applications where prices for coatings would be on the order of $200 per kilogram. So your price for vein graphite is a drop in the bucket, okay? So if it was up to a private person like me, start mixing plant, okay? Then for Sri Lankan industry, develop an understanding as to where your material can be used most beneficially as part of the blend, okay? That's number two. And number three, and I'd like to challenge the audience here, yes, I understand that mining is done at a very high depths, hundreds of meters or 100 meters, right? But we have scalloped natural graphite in Norway. Like I was giving you the example, a place for real men, You either catch salmon or you mine graphite. Same type of scenario. They get graphite from under the ground. 500 meters, not 500 meters, but a couple 100 meters down. Somehow they do it at, $450 to $500 per ton. And they used to be producing 2,000 tons per year. Now they are 12,000 tons per year. So I'm gonna throw it out to the industry. You don't have to do it now, but look at modernization of mining practices. At least create a map, a road map, what it would take for you to make graphite for $700 a ton, your fully absorbed cost, okay? And I'm not saying you shouldn't, you should just go in the market and start undercutting yourself. No, you start with paints and coatings, explore that market. You go into specialty batteries. I hope I clearly mentioned that. You don't necessarily have to go to electric vehicles, but you can go into military batteries, right? So, and military batteries take this graphite and they pay a lot more, right? And specialty batteries, NASA and such. So we can talk about it, right? But I'm going to let my colleagues also speak about it.
I want to just add one thing. I want you to remember that the demand for graphite is not going down. If you look at how the graphite market has shifted for the last 10 years with lithium ion coming on and these other applications, this is not a resource where if you fail to, if you exploit it, it's going to peter off and not be needed. Demand for graphite continues to project significantly as we go forward. So there's risk in everything, but the opportunity here, I think, is worth exploring. And I must agree that finding where you start is not the same as where you end, but breaking into markets and moving it forward.
Thank you. And we have reached almost the end of this session. However,
can you
there's
take,
one.
Can
There's
you take one more
one,
question? Can you take one more question, please?
one online question
Yeah,
is
this
there. Sir, Professor Dilushan, could you please wait one
okay.
second for the online question, please?
Yeah, we have actually two questions from the online participant, Dr. Chamni Miller, joining us from the US. First question is to Dr. Anthony Burrell. What are the potential uses of Sri Lankan graphite in the emerging nuclear industry in the US? And the second one is, how competitive is natural graphite to synthetic graphite in terms of economical perspective?
In terms of what?
So I think I'll take the second one first. Cool. Synthetic graphite is better. I mean, unfortunately, it outperforms natural graphite. However, it's more expensive. So there is a trade-off here, and that's why blends are the approach that people take, and you can jump in on this one. The nuclear one is a tremendous opportunity, but the qualification time for nuclear is very long. So you need very, very high purity, specific, and Katie told me this yesterday, specific orientation of particles so that they basically thermally expand and contract uniformly. There's a bunch of requirements, but the qualification for nuclear is extreme. You think about all of the incidents we've had. This is the one industry that the cost of doing business goes up every time we make a new reactor, not going down. There is opportunities with small modular reactors, but you really need to start soon and be ready to go through those processes of qualification, which are not trivial. The consequences of getting graphite wrong in a reactor are significantly different than the consequences of getting them wrong in a lead-acid battery.
So I'm happy to comment as well. All right, so if you are a graphite company, you must explore nuclear market, okay? You need partnership. Unfortunately, you need to be at 5/9 purity. I don't think you can just get it straight from the mine. You need a partner. You can partner with us. We will purify this material for you. There is some grinding and sizing which is also involved, but the nuclear graphite spec absolutely is very specifically calls for natural graphite. The product is called matrix graphite, and this is for pebble bed reactors. We can take it offline if you like. And just to throw out a number for you, once you have a nuclear graphite product, it sells for $50,000 per ton. 50. Okay?
Right, thank you. The last question by Professor Dilushan Jayasundaram, please.
I thank you very much for that engaging panel discussion and the questions and the comments. I'm Dilushan from University of Colombo. I am what you call a SP simple MA guy. Basically structure property. If required, I do modification for applications. So basically, I think whether we are using graphite or graphene oxide or graphene, we have to be smart in how we are using it. I find I myself was like involved in the graphene research, but when we are involved in it, you see there are fascinating properties in graphite itself, which I wanted to explore. So in certain research, I don't go into graphene. I just do it graphite. And it's fascinating, this material. So that's my overall comment to that. But then I have a question from Professor Barrell. Now you're in the, I think, Rocky National Lab, and you do research, and as researchers, when we do research, we want the best of the purity materials because we want to make sure our prototypes are high quality and they work. But after that, when you are trying to commercialize, what is the model you use? What model you use to get your research from your laboratory into a commercial setting?
So this is a really interesting question. Generally, you're 100% right. When we're working at the laboratory scale, we start with the purest solvents and the purest materials, and we work in the best environments. In my experiences in trying to commercialize things, not as the startup, but working with startups on IP I've developed, the first thing you do is go, how cheaply can we buy the materials? Can I buy 95% hexane and get away with this as we go forward? And then you work your way through that agenda. It's a natural thing. However, when you're working to move into an existing product market, you've got spec sheets, you've got requirements, you've got qualification processes, and while it's always good to save on costs where applicable, you still have to meet spec. So that's a challenge in all of this space. And one of the challenges, of course, in the battery space specifically, but other things, is also how you process as part of the spec sheet. So if you use an innovative process, you're going to have to go through that cost of requalification and doing those sort of things. So the simple answer is, when you move to an industrial product, you've got to meet spec, and then you try and get away with the cheapest materials that'll get you there as possible. But the final product has to meet spec, and that is always the driver for displacing or moving into the industry piece.
Do you do this in collaboration with the industry partner which you have already identified, or you do it within the lab itself?
Yes, and the one that is, there's a couple of options for us, the same as in university. People can take IP and do spin-outs themselves. They have to leave our organisation to do that and go out into the wilderness and earn money and get investors as normal. Or we often will work with companies, in a couple of different ways. One, just in sponsored research to try and help someone overcome a specific problem. So they'll pay for us and we'll work with them collaboratively to solve a specific thing. Or we will license our technology to them and help them move that out into the into commercialization. So all of those options are available, but it really, the key thing is getting involved with industry early and understanding what they really want and what they really need, rather than what I perceive they should be needing.
Thank you. And now we reach the end of this session, this segment, and I would like to give a big thank to all the panelists who shared their views and experience. Let's give a big round of applause to them. Thank you very much.
Thank you very much, Ms. Tilina and all the panelists, for that wonderful discussion. We will now have a short break for tea. So please be back in the room by 5 p.m. after the tea. The tea will be served as the same as the morning refreshments.
Okay. Right. So before moving on to the third team, we will now proceed with certificate presentation for poster presenters. Certificates will be awarded only to students and early career researchers. To award certificates, I kindly invite Professor Sanjeeva Malaviyarachchi and Mr. Drake Thomas. Ms. Oshadi Kaushalya Herath. Mr. Prasanna Jayavira. Ms. Sayuni Ruwania. Miss Abirami Thailanaduraja, Mr. Themiya Kitulagoda, Jaini Bandara, Miss Jaini Bandara, Miss Ruvini De Silva, Mr. Priyanjan Srikanta, Mr. Priyanjan Srikanta, Mr. Harshana Tilakaratna, Thank you, Professor Malaviarachi and Mr. Thomases. Now I warmly invite Professor Patrick McNamara and Professor Kusali Gamage to award the certificates. Mr. Harshana Tilakaratna, Mr. Dileepa Maddumage, Miss Padma Chandrika, Mr. Sahan Uberatna, Mr. Isuru Lakshan, Mr. Tharindu Dasanayaka, Miss Gimhani Nipunika, Miss Shahani Premaratna, Mr. Banuka Gunaratna. Thank you very much to both of you.
Okay, we now proceed to our third theme of the Practitioners Forum, Policy and Regulatory Frameworks related to graphite. To begin, I invite Mr. Nalinda Silva, the Director of Mineral Survey at the Geological Survey and Mines Bureau of Sri Lanka, to speak on the policy and regulatory frameworks related to graphite in Sri Lanka. Over to you.
Okay, thank you, Chair, and good afternoon. I am representing the Geological Survey and Mines Bureau. It means the regulator, and I was asked to discuss and give some insight of value addition, sustainable mining and downstream processing, plus I add exploration as well, because everything starts from there. So I see this in regulator's perspective, but instead of becoming a stringent regulator, I would like to act as a cordial facilitator as well. So this is the policy principles which are very common. You find it, then mine and add value. These are the simple three chain of things that we are going to involve. While doing that, take appropriate measures to safeguard the environment and do research and development that you can have extended opportunities for value addition, even exploration and mining perspectives as well. Then have better legislative, administrative and fiscal norms to run this system properly. So if I try to it a schematic way, find, mine and add value, and build it on your environmental concerns. It can be strategic environment assessment, EIA or national environment policy. We have to adhere these things. And research and development, we are talking a lot of that. Then legislative, administrative and fiscal norms. So on that platform, find, mine and add value. So I keep land ownership bit apart, because that is one of the concerns that we have to take care when we do things in Sri Lanka. Okay, now I am focusing on graphite. Even in a virgin area, you may start with 25 grids, 25 kilometers, maybe square kilometers, then you reduce it to 1 or 2 kilometers and you develop your mine in hectares, maybe 25, 30 hectares. So is the exploration license system working? Well, the third party exploration license system is not working very well. We have, if we consider the number of licenses that the Bureau granted and the mines that opened, so we are not satisfied. So what should be the remedy? A spec company. So if the potential is very high, so can find an international company doing the exploration and transferring that knowledge to the mining sector with profit. Or can EL holders come together and make some sort of a amalgamate and consortium and do the exploration with the state blessing? Then is the land ownership a hindrance? We'll talk about it. What will be the involvement of the state? Okay. If you think about the first phase, I think it must go freely, because you can't think about land ownership. You are thinking about, because 1% of that exploration land going to be developed into a mine. So it is, the state has to intervene and provide free access. Whoever exploring it, it's going to be airborne, it's going to be detailed mapping. Then the next stage is, once you identify the potential, you may moving into that land with exploratory drilling. So then you have to have some sort of understanding with the landowner. Then finally, yes, that mine is developed maybe, let's say, 25 hectares. So that you have to have land ownership, maybe you have to do compensation, profit sharing, or whatever the manner, lease agreements, long term, the land should be yours, unless you're running into real problems. So, fine, okay. Well, we have already understood or mapped the corridors where the potential graphite sites are, because there were all workings. So I put this Maduragoda axis here. So that is one of the prime targets. Then the southernmost part of the Maduragoda axis is Kahataga. What we mapped, my friend Lasanta sitting over there, he did all the mapping. So if you want to, before you dive into that Kahataga, it's better to have a view of we have prepared a very detailed 3D map of that existing veins and all. So it is Lasanta's work, so you better consult him before diving into Kahataga. Okay? Then we have developed by our own for shallow targets, VLF, SP and IP. Whether we can create something like this with that only for shallow targets, yes. We are confident about our exploration strategy, but it has to be tested with ground truths. I think Margosa people will provide us details of their boreholes. We can run this integrated system and make sure we can find at least shallow targets. Okay, when it comes to mine. Yeah, well, the first requirement is you have to have land ownership or lease agreement, at least land consent. Then environment recommendations to start mine from exploration. I think if you consider graphite mining, it is a small surface footprint, maybe 3 by 3, 1 or 2 shafts. Interesting parties, environmentalists may not knowing what is happening in the subsurface. So it is, if you compare with surface mining, that is an advantage. But again, if you think this cartoon, so where the mining ends, because we have issues on the land where even the land premises are not properly identified in many cases. So how are you going to find it in the subsurface? It remains as an issue. But as far as you don't draw down the neighbor's shallow well, mining may go. Okay? But again, there are some extreme examples, slant drilling. So I'm not going to explain it further. So it can lead into wars, even not simple disputes. Okay. So add value. So you'll find, you'll mine, then you add value. I think value addition, there are a lot of discussions here, but the white side of it, high quality material. So the black side of it is high operational cost. So if you put, just observe in the web, we are the single supplier, unknown quantities, and land ownership issues. So this can go either way. If you manage properly, you can have industrial monopoly, because we are the single supplier, or it can be a single supply syndrome. I mean, the investors may not come here. So unknown quantity, again, it can be a boom, exploration boom, or it can be depleted investor confidence, because they don't know how much of material there. So land ownership, private lands may be hindrance, maybe you can have direct ownership. So how you manage, how you deal with this each and every aspects, it may end up in white side or maybe gray side. Okay. So this is, I think, I'm going to put it in one slide. Or steady supply, this may be Bogala, Kahatagaha, Ragadara, X and Y. It's going to be in-house, because where the graphite is. I mean, exploration and mining is here. But when this is very important. Product that only vein graphite could be the raw material. We call it high-end specific applications. And any process that flake graphite could be the raw material, general purpose, don't just leave it behind. Maybe only Vein graphite is the lowest quality. Yeah, you can go for EV batteries, but not the material that we are talking about, because yeah, supermagnets, radar absorption material, there are a lot of things that you can, I'm not mention graphene here, Manju is not here because he'll take 2% of material and the rest of the 98 we have to deal with it. So, I mean, yeah, it is on the card, of course, the graphene. But again, the EV and the internal combustion engines, I think we are losing if we go for EVs, because lithium ion battery, it's having the same energy density if it is, if it is manufactured with flake or vein. So don't waste vein there. So you have to be careful. So the next thing is, how far we are doing our business here. So the steady supply, mining and exploration, it has to be done here, of course. The material is here. So beneficiation, processing, product development and marketing, of course, the market is there. So how far we are going? Processing, product development, we are going to do it here. I think again, my friend Manju is moving to Turkey and India. I told him that with operational cost, that will happen. So we have to think it critically, why our production cost is high. So we have to act accordingly. So again, people a lot talking about porcelain industry and try to compare it with maybe graphite, vein quartz. Yeah, because ease of freight and communication connectivity made the national boundaries immaterial for mineral value chains. Because if you think in-house production, if it is costly, we are going to lose our comparative advantage. So we have to think differently. Okay, again the quality. What is quality? Because quality depends on the end user. So the quartz industry, it has happened. We are having silicon dioxide 99%, but if you have aluminum 40 ppm in the structure, you can't use it for solar cells. But still, we can say in a silicon dioxide percentage, we are having one of the best quality material. So it again depends on the end user. What we are looking for here is, I have written it, the comparative edge of Sri Lankan non-metal mineral is the quality. Yet as of the comparative setting, initiating of industries based on the quality is a complex affair. However, wherever the material is plugged into the mineral value chain, the due dividends that owe to the intrinsic quality of material shall retain. The God-given value is there. So we have to do business in a way that it reflects and the dividends are coming back to the country. So again, if I focus on this value chain, where are we going to address our material? It depends on the comparative advantage. So this is our comparative advantage. This is mapped for, we did this mapping for vein quartz, but later I understood that it is also somewhat comparable to vein graphite as well. So when it starts on the pit head, we have high value because the material is okay, it's nice and fine. But when we go with downstream, beneficiation, processing and product development, well, as of the contemporary issues right now prevailing here, we are losing it. So we have to, either we have to find a way how we can make this curve this direction, maybe low energy cost, maybe the constituents are brought to a country with lesser tariff. So we don't know, we have to think about the system. Unless with this particular settings, I think we are not going to produce end products here, even processing going to be limited. Because if we think about centralized processing, to bring part of the centralized processing in the centralized, the central setting into the periphery, it won't happen. The reason is that if you think about eastbound freights, that going from Sri Lanka, the countries of Asian organization and China, it is going for nothing because all the freight, the containers are empty. So anyone can find very low cost to send material there. So we have to take all these things into account when we talking about value addition. So again, this what we want to see. We would like to slide this to end here, but we have to do a lot of things, because people telling 1 kilo of graphite is 10 rupees and 1 kilo of graphene is 10 million. Okay, nice stories, but how are we going to go there? We have to think. Okay, then the fate of Wayne graphite EV and ICE vehicles. Though it is polluting the environment for our graphite, we would like this ICE vehicles, internal combustion engine, because it needs a lot of lubricants, it needs carbon buses. But when you go to EV can make, the battery can made of the flake graphites, which are comparatively cheap. So the future, how we think, I don't know. I later found that it is a B2. But anyway, I think it is a big bird, and you have some sentimental ideas as well. But what I'm going to put here is, let's say the graphite can bring it can use as a radar absorption material, and it can minimize the footprint of it. And again, I think people thinking about it, its electromagnetic properties. This bird is big, maybe a small bird. It can run, let's say, self-propelled and self-energized, because the graphite is having electromagnetic properties, can act as a battery, seek heat and everything. So it's going to be a bird that you can't see, radar can't see, and self-sufficient. It means self-sufficient, invisible, it make invincible, I guess. Okay, thank you. So this is my abstract. So if you like, I'm here. I can take questions. Is there any time? Enough time? Thank you. Okay, thank you.
Thank you, sir. So we will have a Q&A session after our next speech. So next we have Mr. Nate Jones from the U.S. State Department's Office of Critical Minerals, who will be joining us virtually to present on the policy frameworks in the United States.
Thank you very much. Well, good afternoon, everyone. It's a pleasure to be with you. As the host said, my name is Nate Jones, or Nathan Jones, and I am a diplomat in the State Department in the Bureau of Economic, Energy, and Business Affairs in the Office of Critical Minerals. It's a really great pleasure for me to speak to you today. I wish I could be there in Colombo with you. Years ago, I spent quite some time in Colombo as a diplomat, and so I know it well, and I would love to have the opportunity to return again one of these days. But as it is, I can speak to you this way, and I just wanted to give you kind of an understanding of the framework of how the United States is looking at critical minerals currently. You all are the experts in the graphite sector, on the geology of it, the science of it, the applications of it, the mining of it, all those things. But I'm going to speak more broadly about critical minerals, and not specific to the graphite that Sri Lanka has, but hopefully that kind of helps you understand the context of how we are looking at critical minerals across the globe. As you may know, the United States has a broader definition of critical minerals. Our geological survey has a list of about 60 critical minerals currently, and other agencies that have additional minerals that they look at closely as well, if you're talking about the Department of War or the Department of Energy or some of those. So there are a lot of minerals that we look at, and it's a big job to tackle that list and to try to address the challenges there. But again, I want to talk about some of our general approaches on critical minerals. Obviously, we all understand how important critical minerals are, and rare earths, that they are essential for our advanced technologies, and that these needs will become even greater as AI, robotics, batteries, and autonomous devices really transform the economies that we have. Securing these critical minerals and rare earth supply chains ensure that we have access to, you just asked me to turn on the video. I'll try that. Let me know if the signal is still good enough, but we can try that. Okay, how's that? All right, so these critical minerals, rare earths, all of them, the supply chains ensure that we have access to the minerals and the derivative products that are essential for United States defense, energy, industrial, and technology sectors. And we also know that it's no secret that the key aspects of this market are very concentrated in a single country. And that country does not follow free market principles, and that causes vulnerabilities to the United States, to our economy, and to the rest of the world, as we are subject to these non-market supply chain disruptions that can occur. As Vice President Vance has said previously, the international market for critical minerals is failing, and supply chains remain very brittle. So what do we do about this? To resolve this, the United States intends to build new sources of supply, foster secure and reliable transport and logistics networks, and to transform the global market into one that is secure, diversified, and resilient from one end to the other. So to achieve this, international cooperation with allies and partners to insulate these supply chains from non-market distortions is critical to U.S. reindustrialization, supporting our own mining and processing sector, increasing our own critical mineral stockpiles, and reducing our dependence on non-market foreign suppliers for these resources. But in doing so, it will benefit the market in general and for all of the countries that are involved in this. So we want to establish a marketplace of trusted buyers and sellers that reflects the real cost of extraction, recycling and recovery, processing, and trade of critical minerals and refined products in a market-based economy. As Secretary Rubio has said, our goal is to have a global market that is secure, a global supply that is enduring and is available to everyone, every nation, at an affordable price. We want to correct for non-market price distortions. We want to drive private investment in minerals extraction and processing, and the projects that are owned or controlled by U.S. or other trusted partners. We want to ensure that all parts of our critical minerals and rare earth supply chains are insulated against future economic coercion. It's a big job, and it's a challenging task. So how are we approaching this? Well, the Trump administration's policy on critical minerals centers really around 4 pillars. First, we are investing in mining projects. Second, stockpiling minerals. Third, we are protecting our mining companies and investments abroad. And fourth, we are rebuilding our domestic mining sector. So let's go into each of those just a little bit more. On investing, the United States government is now deploying hundreds of billions of dollars of capital into the mining sector between debt and equity. And I believe a speaker mentioned this a little bit earlier. We are doing things that the American government has not done before in terms of investing in these sorts of projects. We are doing equity investing so that we can get deals done quickly and move forward. We are making sure that the United States has a roadmap for every mineral we need to power our economy. On stockpiling, we have a defense stockpile, and we're actively working with our private sector to stockpile minerals for our civilian economy as well. Project Vault is something that we announced recently. It's a landmark initiative that establishes a domestic strategic reserve for certain critical minerals. The Export-Import Bank of the United States has also approved really a tremendous amount of financing for these sorts of projects, up to $10 billion. This work is designed to shield domestic manufacturers from supply shocks, expand our U.S. production and processing of critical raw materials, and really just fundamentally strengthen America's critical minerals sector. We have let that sector atrophy over the past decades, and it's something that we recognize we need to fix and we need to address in order to secure our ability to expand our economy and continue to grow the way that we need. Now, we know also that it's going to take work with partners around the world. And we're hopeful that we can get U.S. companies and investors involved in those projects overseas. So that's the third point of this is protecting U.S. mining companies and investments. We know that the mining industry has a problem with commodity pricing caused by strategic overproduction and price dumping. We've all seen that on the market across a range of minerals and metals. We're having nearly daily conversations with our international partners about how to protect our collective mining ecosystems from this state-subsidized competition. And we'll talk a little bit more about that in a few minutes. Last on these four pillars is mining sector reform. The mining industry in the United States is challenging. And so we're making critical minerals projects in the US our number one priority right now. We have a federal priority list for permitting, and it's going to move much faster than the 29 years it has previously taken to build mines. It's one of the longest timeframes for mining projects in the world when you look at the time from deciding to start a new mine to the point where it is actually operating, due to a range of things, but primarily regulation at both the state and the federal level. A number of different factors go into making that time frame really unworkable because it's so long. So what are some of the things that we at the State Department have done about this? On February 4th this year, Secretary of State Marco Rubio hosted a critical minerals ministerial here in Washington, D.C. At that event, the United States was joined by 54 countries in the European Union to collectively take action to build secure and resilient critical mineral supply chains. At that event, we announced U.S. government financing opportunities to support strategic minerals projects. These efforts are complemented by our collaboration between the United States and its Pax Silica partners to secure strategic stacks of the global technology supply chain. As we look at the different sectors that these critical minerals go into, the high technology and microchips and those sorts of applications are one of the key elements that we're looking at. At this ministerial, Secretary Rubio also announced the creation of FORGE, which is the Forum on Resource Geostrategic Engagement. So FORGE is a successor to the Mineral Security Partnership that you may have heard of, the MSP, which includes now 16 countries plus the European Union as in the form of the European Commission. FORGE will be chaired by the Republic of Korea through June, and then we'll move on to a new chair. And this group will lead with bold and decisive action to address ongoing challenges in the global critical minerals marketplace. Understanding the benefits of working together and building on the Mineral Security Partnership, FORGE partners will collaborate at the policy and the project levels to advance initiatives that strengthen diversified, resilient, and secure critical mineral supply chains. In addition to this, the U.S. government is working with partners to develop a ring-fenced preferential trade zone of countries who will join the United States in pursuing coordinated actions. As Vice President Vance said, we want to eliminate the problem of people flooding our markets with cheap critical minerals to undercut our domestic manufacturers, something that we've seen in action repeatedly. These actions that we're planning to take include adopting high standards-based systems and pricing mechanisms, strengthening investment screening, implementing market reforms and investment facilitating regulatory practices, and mobilizing investment in mining, processing, and recycling domestically and in partner countries. This strategy will also support seabed critical minerals extraction, which has a longer commercial ready time horizon. That's something we're still working on, and it is going to require more investigation and more investment. So that's something that we're definitely looking at as well. Now, building on the progress that made at the February ministerial that I spoke of, the U.S. Trade Representative's Office is now working with partner countries to develop this ring-fenced preferential trade zone of countries. This work, these negotiations, include the development of bilateral action plans, and we've seen some of those announced already. There was one with Japan announced previously, and just last week was the announcement of an action plan between the United States and the European Union on critical mineral supply chains. So those action plans and all of this effort will lead to what the U.S. Trade Representative is negotiating now and working on, and that is the conclusion of a binding plurilateral multi-country agreement on trade in critical minerals, which will incorporate the idea of some pricing issues, some pricing protections, and preferential trade zone. So that's kind of a brief overview of where things stand at this point and where we are headed. And I hope that gives you kind of a sense of where Sri Lanka's assets and Sri Lanka's resources potentially fit into that structure of the steps that we are taking. And so I'll conclude there for now and see if we move on to questions.
Thank you very much. So now we open the floor for the final discussion and Q&A session. You can ask any question from both speakers.
We have an online question for Mr. Nalin. The question is, how are mine closure and post-mining rehabilitation currently regulated for graphite operations in Sri Lanka? And are there any standardized requirements for long-term monitoring?
Well, there are only 2 mines in operation at depths. So still they are in a they are functional. So all the mines that we talk about is small pits that only it won't extend into the much into the subsurface. So yes, but now we know that there are mines are coming up. So when we granting a long-term mining license, it is the rehabilitation plan is part of it. Because as I explained, the land ownership and the environment concerns are considered to grant the mining license. So the rehabilitation plan is a part of that environment concern. Need further clarifications? Okay. Yeah.
I have a question, Mr. Nale. This is regarding the recently opened the mineral policy. So the general public regards the mineral resources as the wealth of the country. So my question is, under the mineral policy, what are the measures taken to safeguard the mineral security, as well as what is protected chiefly under this policy?
Well, it is, broad question, but when it comes to radioactive mineral, the Act says that it is a protected mineral. So it has to deal in different manner. But if you are talking about the due dividends, and then, yes, under mineral policy, the value addition has been introduced. So whoever engage in mining, then they have to go for the next step for value addition. The miner itself need not to do that, but if you think about export, how we export, then we put benchmarks and threshold values just to bring the due dividends. That's how it works.
Who is responsible for valuations?
What do you mean valuation?
Once you have a deposit, or for example,
well,
if you discover a new one?
Well, we'll see that the system is open. I'll explain with vein quartz. So there are a lot of, because graphite is an extreme sort of example, because very few engage in graphite mining because it required a lot of resources. But if you think about something like vein quartz, so there are over many hundreds of mines, a very small category. If there is a vein quartz in your backyard, you can have a small license. So the environment concerns are considered in a lower level. So you can produce that material. So once that material can move freely, but once it goes to the industry and when it goes to the export market, then they have to provide the threshold values. As of the threshold values, you have to pay the royalty. As of the degree of value addition, you have to pay cess, and also it is regulated in a manner when it comes to the export market, because weighing cost is easy because nearly 95% of material is exported. The other mineral varieties goes to the industry, and the dividends comes as when the industry make end products, maybe tiles, maybe ceramic, so the dividends comes through that.
Excuse me, Nalin, this is Dilushan here. Now value addition, when you, I'm here, okay. So value addition is not like a individual thing, it's a combined approach to value addition. When you decide on the policy side, have you identified who should be doing the value addition, who are the involved partners should be, anything like that?
No. Let's say when it comes to value addition, what as regulator is doing is providing equal ground, because leaving all the restriction and the competition to decide what best. Because let's say if we have bad experience in mineral sand, because in 2012 there was a cabinet paper telling that with mineral sand you have to do this and this, unless you are not allowed to mine and market it. But some of the targets could not achieve in-house, because I have explained it, because the production cost is high. Then what we looking is the open competition. So if let's say if our vein graphite is highly valuable, then people come here and do value addition. But as I again explained, if that value addition could be done somewhere else for cheaper opportunity cost, then it will go there. So this debate came, I'll take 1 minute. Then there was a argument, if you produce graphene, okay, if I give 1 kilo of graphite, the same material to industry here, India and China, so idea is that China can produce it lower cost. Then the answer came that the material is ours, so can we have a restriction? The problem is that we are not only producing graphene or graphite, because we are into other industries as well. So we buy material from outside to run our garment industry as well. So they can impose tariff, then we are out of business. So this is buying and selling open market. So we have to think in that manner.
So,
yeah. Yeah, of course. Well, I think if you can run a venture with profitable manner, you can sell it. I mean, the government is not going to put restrictions. I mean, even graphite, as I understand, graphite is even not subject to tariff. So there is a tariff imposed on us. I mean, not only us, many other countries on the current US administration, but graphite has been exemption, as I understand, because the reason is that they all understand the value of this critical mineral. If we can produce it a way that we can compete in the market, is no one going to stop it, that the system will run. Yeah, well, I'll tell the No, the problem is here, even Kahatagaha time to time, though it is very good quality material, time to time find it difficult to sell. The reason is that we have to establish continuous supply chain. Unless the buyer is very anxious that he doesn't know whether the next shipload is coming or not. So that is what we are looking for, at least 6-7 mines that can produce not only 3,000, but we are looking of something like 15,000 metric ton per annum. That is only, enhance the confidence of the buyer. So that is why we are stuck right now. That is, we need some exploration. We want to open few mines. I'm happy with Margosa, and Mr. Kirti is there, is trying his best, and Bogal is okay, but Kahatagaha we are going to go with EOI to develop it. So we have to make sure that, as I explained in my slides, we are the single supplier. So we have to make sure that the material is there, unless no one is coming here. No, sir. The issue is, if we can guarantee, not only to US, to the open market, that there are enough quantities of vein graphite, and they are going for the extreme type of production only the vein graphite can address, then the both side has to be a security. Their security is that there is enough material to run the business at least, let's say, 15 years, unless who is going to build that technology? No, just assure the material, the material supply, that there is enough material, then the business will run. So you can't do it individually. It's going to be an effort of the whole state. Okay, thank you.
Thank you very much, sir. Sorry about that. Because of the time constraints, we have to stop the session. I think you can join tomorrow, and we can continue the discussions. So with that, we have come to the end of the Practitioners Forum, and I would like to extend my sincere gratitude to all the distinguished experts, panelists, and organizers, and the participants. And to conclude the session, I cordially invite Ms. Tilna Kumari Kandanamulla, Senior Scientific Officer at the National Science Foundation, Sri Lanka, to deliver the closing remarks.
Thank you. And if I quickly give a quick overview of this session, we had 3 themes. One on research, where we looked at the graphite-related research landscape in both countries, Sri Lanka and USA. Then the theme on industry needs and market perspectives, where valuable discussion and brainstorming was done on resource, technology, value addition, and international collaboration. Then the third theme was just now concluded. It was on the policy and regulatory frameworks and mineral policy of Sri Lanka, and different perspectives related to industry and partnerships, along with the perspectives of the USA, were discussed. As the way forward, National Science Foundation, in collaboration with our co-organizers, wishes to pick policy relevant points and make a compilation to bring into the focus of relevant policy makers and policy making spheres. With that note, I would like to thank sincerely to the following organizations and personnel who supported to organize and conduct this session successfully. First of all, I would like to thank Professor Kusali Gamage, expatriate Sri Lankan scientist from the USA, for your unending support and guidance and all the input to organize this session, along with the team of the academics and researchers of the Department of Geology, University of Peradeniya,
led by Professor Sanjeeva Malaviarachi and the esteemed researchers. Not only that, I'd like to especially thank the speakers, presenters, and the panelists who shared their views, shared their knowledge, and expressed their views regarding different aspects under these three themes. And I would like to sincerely thank them. They supported to make this event a success. Finally, I would like to thank the team from the National Science Foundation of Sri Lanka, starting from the chairman, Director General, Additional Director, Head and the scientific officers from the Research Division of NSF, as well as my team back home at the International Affairs Division at the NSF, who contributed in every aspect to make this session a success. Thank you very much.
Thank you, Ms. Kandanamulla. We now invite Summit Chair, Professor Kusali Gamage, to deliver the closing remarks.
Thank you, Eranji. It's been a long day, and I see my US colleagues are falling asleep. So, as we conclude day one, I'd like to thank all our speakers, panelists, and participants. It has been a very engaging and productive day. Before we wrap up, I kindly ask you that take a few minutes to complete the day one feedback survey using the QR code that Mr. Udara will put on the screen. Your input will help us make necessary adjustments for tomorrow's session. There's the link. After completing the survey, we invite you to join us for the poster session that's going to be on the next building, the pink building, which is the geology department. And one final reminder, tomorrow we begin at 8 a.m., not 8:30. So please be here on time. Remember to bring your name tag with you. In the afternoon tomorrow, you will have the opportunity to have a more focused discussion on different topics in breakout sessions. So please come prepared with any questions that you may have so we can continue the discussions we had today. With that, I thank you again and enjoy the poster session and have a great evening. Thank you.